Hi everyone, it's Rohan this side. And now that you're watching this video, I'm sure you're over here to understand what kind of web application you will be able to create by the end of this program if you're going to enroll into it. So yes, let's get started with a quick walkthrough about this application in this video. So one of the cool things that you can do with this web application, and that's my personal favorite, is to colorize an image of the galaxy that is in the Galaxy Zoo dataset format. So that's how the Galaxy Zoo dataset format is going to look like, which is the project from Zooniverse, which is having collections of different galaxies taken from different astronomical surveys like SDSS. So what is the main job of this application? It's going to take an input from this kind of Galaxy Zoo dataset, and then once I give an input to this, it's going to check if it's a black and white image or not. If it's not in the black and white format, it converts this into the black and white format, and then this is going to be passed as an input to our AI model, which is responsible to give them a color. So if I look into this is the kind of output that my system is giving me. Okay, this is the AI generated colorized image. Let me give you one more example. So let me pass this as an input, which is having a completely blue color in the galaxy in the center. Let's see if we're able to reproduce this. Yes, we are. Let me give you one more example. Let us choose some spiral galaxies that we can see in our data set. I guess I just saw over here. Let's see if it's able to get the same color over here or not. So yes, as you can see, this is the kind of thing that we can do. The other cool thing that I can do is you can generate a new galaxy image by clicking on refresh. So it's going to give us a new galaxy this time. Now you might be wondering that it's not looking like a galaxy. Well, the dataset that we have chosen is again from the Kaggle, where we are having a different looking galaxies that we have captured over here from Earth via different telescopes. And you can see that these are the kind of images that we are having in the dataset. Okay, these are the kind of images that we have in the dataset. And then a similar looking galaxies we will be able to create over here by clicking on refresh. You might think that we are taking a random image from this and displaying it over here. That's not the case. This is completely generated image by AI from scratch, from random numbers. When I'm clicking on refresh, it's taking the random numbers as an input and producing this galaxy like how we had seen over here in the data set. And then I have combined both of this kind of APIs. And then if I want to colorize it, even though this is not from the Galaxy Zoo dataset, but if I want to colorize it, I've given an option to do this. I'm passing this as an input to that second API that is to colorize an input, which is already in the black and white format. So it takes that as an input and gives you this kind of output. And you can see that because of the disturbance in the background, there is a kind of a redness generated. I can demonstrate this going back into our original, the colorization API and get you an image with this kind of noise in the background. I guess the last image I guess this is the fine. This is the one image that I can take. So over here, it is having a noise as you can see, but then the shape of the galaxy and everything is clearly visible. So you can see that this is the kind of output that we are able to generate. So yes, this is the cool web application that you will be able to build if you're going to enroll in this particular program. Hi everyone, I am Rohan from Spartificial, and this program is brought to you by Spartificial, that is GANs for Astronomy. And I hope that by now you have watched our previous video where I've given you a walkthrough of what is the final web application that is powered by AI that you will be able to create by the end of this program. And then in this video, I'm going to help you understand that how you're going to achieve that. So basically, we have divided this whole program into 8 different modules. Starting from the first module, we're going to have a proper idea about what is the meaning of the generative adversarial networks and what are all the kind of components associated with this generative adversarial network or GAN in short. Now with this idea of the GAN, we are going to go ahead and create our first project, that is to generate the galaxies with that GAN. And then in this output, you're going to see that there are certain kind of problems. And to solve that problem, I'm going to introduce you to a new version of the GAN called as Wasserstein GAN. And along with that, there is one more version called as Wasserstein GAN with gradient penalty. So with the help of that Wasserstein GAN with gradient penalty, I'm going to help you see that this time the outputs are trustworthy. So that's what will be covered in our module 4. And then we are going to move on towards our second component of this program, that is image to image translation using GAN. And the one that we're going to use is called as pix to pix model. Over here, we're going to learn about how the inputs and output structures are going to be, and then how we can build it together in the Python. And then in module 6, we're going to go ahead and get our black and white images of the galaxies, pass it to our AI model, and it should be able to generate that colorful images. And then in module 7, I'm going to help you understand what are APIs, how to build an API with the help of FastAPI. And then to build that front end, we are going to use Streamlit. And the code for the Streamlit, I'll help you understand how within just few seconds you can get this directly from the chat GPT. So all of that kind of things are covered in our module 7. And now that we are having the model which is already trained for the generation of the new galaxies and colorizing them, we can use those saved models and create API endpoints out of it, and then visualize all these kind of things with the help of Streamlit frontend. And that is going to be covered in our 8th module. And that's where you will be able to create that web application that I had shown you in your previous video. So I hope that all of you are excited to get started. So yes, I'll see you in your first module.
Hi everyone. So before we actually get started with our first module in this program, let me tell you what are the prerequisites that you will be needing so that you can complete this program without any problem, without being overwhelmed. Okay? Because trust me, if you are not having these prerequisites clear, there will be a lot of chances that you become completely clueless of what's happening. All right. So what are these prerequisites? And let's say just in case if this kind of prerequisites are not tick marked for you guys, and if you have purchased this course, what are the things that you can do in order to cope up with that and get this kind of things checked for you and then continue in this program. Okay, so even let's say if you have purchased this particular course right now and you might think that, oh my god, I don't have these prerequisites, I'll tell you how you can cover this. And for the people who are watching this video before actually enrolling into this program, please know that these are the things that you will need to enjoy this program throughout, or else you might have some difficult time while I'm explaining some of the concepts. Okay, but yes, as I mentioned, I'll tell you how you can cover up those these prerequisites, and then continue in this program. Okay, so let's first talk about what are the prerequisites that we expect you guys to cover. The first thing is how to code using Python, and the basic concepts of the Python programming. So over here, I personally expect that you guys know the meaning of for loop, while loop, right? The conditional statements like if, elif, else, right? That kind of things. Then how do you define a function? How do you call a function? So this kind of Python programming knowledge is required. All right. I won't be explaining you in the while going through this different projects in this program, I won't tell you the meaning of the for loop or the while loop. I expect you guys already know it, and then over here I'll explain you why are we using it, but then how is it being used is something that you should know. Okay, so how to code using Python is there. The basics of the Python program is what we expect. Okay, and then the second thing is the fundamentals of the deep learning concepts. So over here, we expect you guys to know the theoretical knowledge of the deep learning, as in, let's say, what are the meaning of neural networks? What is the meaning of different types of optimizers, like gradient descent is there, stochastic gradient descent, ADAM, RMS prop, and the list can go on. You should know at least one of these algorithms, let's say, for example, gradient descent. Okay, or at least an idea about the optimizers. And then you should know about activation functions, right? So these are the kind of theoretical knowledge of the deep learning that you must have. And on top of that, if you have solved any of the projects in past, that is going to be just adding a cherry on the top. But yeah, that are the kind of prerequisites that we need to have before you actually get started with this program. Let's say just in case if you are not having this kind of things covered, then what you can do is you can check our other courses on the Udemy that exactly teaches you the same thing. On top of that, you are going to solve some additional problem statements and bag extra projects for your portfolio on top of this G4A program, that is the GANs for astronomy. So the course that I'm really going to recommend over here is this one, the Artificial Intelligence for Lunar Exploration, where we start from the basics of Python and go to a very advanced level of AI where we talk about image segmentation. So over here, if I show you, in the second module, we are having the master of the basics of Python, where we talk about the functions. In the control flow, you have while loop, for loop, then the condition statements like if, elif, else, right? And apart from that, just see how many different things you're going to cover. So yeah, this is going to help you a lot. And then there is a module of deep learning. So here is the theoretical problem that we are solving, and then the implementation of that using the keras. So all these kind of things will make you super ready for this program. Okay. So just in case if these prerequisites are not covered, there is no problem. If you are really interested in the generative AI and how do you work with this in terms of images, especially astronomical galaxies and everything, then this course is for sure you can take. But in case if these prerequisites are not covered, you know what to do. Alright guys, so yes, I'll see you next in the first module, and hope you are going to have complete fun throughout this program.
Hi everyone. So I welcome you all to the first module of this program, that's GANs for Astronomy. And the main theme of this module is to help you guys become very much comfortable with the concept of GAN. And for that, I have divided this module into 8 different videos. The first video is about understanding what are the different generative models and where GAN places into that all the kind of generative models. Now, once you're having the idea about different models that we use in the generative process, we are going to go ahead and look through some different examples specifically for the GANs part. Now, once you understand the capabilities that GANs have, in the next video, we are going to dive into the introduction, that is the theoretical understanding of GANs. So that's where you're going to understand an overview of how GANs actually work. And then to dive deeper into it, we are going to look through the architecture that we have in the GAN, where we are having the generator and the discriminator part. So a proper idea about that will be explained in the fourth video of module 1. After that, to train our GAN, it's very much different as compared to what you might have seen in different training with the help of, let's say, Keras framework. Over here, we need to set up our own training custom loop. For that, you need to know the loss function. So we're going to cover about the loss function, how to get the balanced training, because GAN has a problem of unstable training. So how to get that balanced training, how the output should look like, that will be covered in the next video after that. And then because we're going to have a custom training loop, we also need to have an idea about the optimizers and how to apply it. Once we are done with all these kind of techniques, we are also going to address some of the problems that are associated with the GANs. And trust me, there are a lot of problems with the GANs. Yes, I'm also going to give you the solutions for that throughout this whole program. But yes, for now, that's what is covered in this module. So I hope that all of you are as excited as I am to get started with our first module. So, my dear friends, I present you the flowchart of generative models. Jokes apart, guys, let's concentrate. So, we are having the flowchart of generative models, which is further categorized into explicit density and the implicit density. If I talk about the implicit density, over here we're having the direct examples. The one is called direct and the Markov chain. And in this direct, we are going to talk about GAN throughout this whole program by solving a lot of different kind of projects, cool projects. Okay. And then in the explicit density, it is again categorized into two different things, tractable density and the approximate density. And then for the approximate density, we are having the respective categories with examples. Now, my main aim over here is to not explain you about all these kind of examples because all of these are different generative models. I am going to focus on the main terms, the main keywords. And how am I going to explain this? I am going to explain it with an analogy that let's say if you want to cook some kind of biscuits for yourself, how you can do it with multiple different ways. Okay, that's how we are going to understand this whole thing. So in this flowchart, the main thing is to understand about generative models, right? So to give you an analogy over here, think of that you are having some kind of recipe book, okay, and that recipe book is having some kind of magical powers that you will always learn from all the biscuits that you have ever tasted. Now, what's that magical power that this recipe book is having? Based on the taste that you are having from all the kind of different cookies that you've had so far, it can create new cookie recipes that's going to taste similar to all of this you have liked before. It's similar. Okay. And this is exactly what a generative model does. It learns from some examples and creates something that is new based on the knowledge that is grasped by looking into the examples. So that was about the generative models. Now, to generate different things like this, there are two different ways. Let's first talk about implicit density. So suppose that you are having a biscuit recipe that exactly tells you how much amount of ingredients are going to be there. And this clear and precise information that you are having in this recipe is what defines explicit density, which is basically giving you a detailed formula to follow from which you can generate these random samples. Now, whereas if I now talk about the implicit density, over here you can think of it as like, let's say you're imagining that you are having a special biscuit jars. Okay. Now, this biscuit jars are in a way having some different varieties of cookies. Again, very similar to how you have tasted it all your life till now. Now, without having an exact knowledge of what different kind of biscuits are present in that jar, okay, what you do is you put your hand into that jar and get one biscuit out. It's guaranteed that every time the biscuit that you're going to grab is going to be very similar to what you have tasted in your whole life till now, but you are not really sure about what kind of biscuit that will be. Okay, you don't know about ingredients, you don't know about exact formula to follow. Still, the magic over here is that every time you're going to put your hand into the jar, it's going to give you this kind of biscuits that taste just like that. So that's about implicit density. It doesn't give you exact details, but gives a general idea of what to expect. And guess what? That's exactly what we're going to learn with GANs. It's going to be fun, trust me. Now, let's say inside the explicit density, I'll just explain two more terms and then we are done with this video. So, yeah, what is the meaning of explicit density? It's a way where we are exactly aware about what to produce. But now there are two more categories inside this. Let's talk about tractable density first. Okay. So over here, you can suppose that you are having um, a biscuit recipe that's very easy to make. Or let's say it's not that easy to make, but the recipe that you are having is having a detailed instructions, which is not very complicated to read. You can follow them without any hassle. You're having exact ingredients mentioned over there in what quantity. So it becomes very simple for you and straightforward to work with that recipe to produce whatever you want. And this is what is called as tractable density. Whereas when I talk about the approximate density, what's going to happen over here? Let's say that you want to again bake some kind of biscuits for you. Now you're not having an idea about the exact ingredients to follow. Okay, nor you are having any kind of exact method to follow. You know that approximately if you follow this kind of a guideline with, let's say, whatever kind of ingredients available to you, okay, and then you are trying to prepare a cookie, so what's going to happen? Obviously it's not going to taste perfect like what you have if you're exactly following instructions with the quantities and everything. Still you're going to approximately get the same taste. And that is exactly the case with the approximate density. All right. So I hope that I was able to give you some kind of an idea about different ways of generating stuff. But I first talked about the generative models, overall what it means. Then I further categorized it into explicit density, where we are having some kind of a way to follow to generate a data. In the implicit density, we don't have any kind of way. We just have the data. We have to look at the data And randomly, we are going to generate this kind of data. And that's what we are about to do in the next module by using the simple GAN, the simple generative adversarial network. Whereas in the explicit density, you're having two different ways to get or to generate some kind of data. In tractable density, you are already aware about some probability distribution. Okay. From there, you are generating some samples. In the approximate density, you don't exactly have the idea of the probability distribution, but you can still approximate it by some ways. Okay, so that's the whole idea about the generative models. And our main goal is to understand much more about GAN by solving multiple different examples in the field of astronomy. So let me take you on a journey of understanding what kind of outputs you can produce with the help of different GAN models. And I've got these three links for you to try out. The first one is this, the second one is this one, and the third one is this. So let's go on to the first one. Now, this is a very classic example of the basic GAN where you go ahead, give some kind of random inputs, and it's going to give you some random output as well. Where over here, the data set on which it is trained on is the images of human beings. Where if I give some kind of random numbers as an input to that model, the output will be some random person. And this kind of person in real life does not exist. Similar to this person, there are some kind of features of the eyes of some person, the feature of the nose of a different person, then the feature of the mouth of a different person, the hair, the ear style, the collar that you can see over here are taken from different kind of personalities from the pool of data set where we are having different people, and then randomly it's taking this kind of features and creating this kind of image. Now if I refresh this, a new image is going to come. Again, this person does not exist. Again, if I just refresh this is another person. Just look at the quality of the output. I again refresh it. That's one person. That's a baby actually. And if I zoom in the bottom part, you can see that it's trained with the help of style GAN 2. This is a version of a GAN. Okay, I'll just refresh it once more. I can see some image might not be that good, but most of the images that we'll be seeing will be just amazing. So that was a very impressive thing that I really wanted to show you. Like this, you can create your own web page where if someone is going to come to your web page and run it or reload it, it's going to throw you this different images of, let's say, whatever you want to show it to them. Right. So that's one example. Now, one of the project that we are having in this program is based on image to image translation. Okay. Over here, if I show it to you, this is called as pix to pix paper. So a lot of different examples of this pix to pix paper is given to you over here. Some of them I have drawn it. For example, this shoe, I have drawn it. This is given, if I click on random, this is going to be generated automatically. Then even this was given, right? But the whole idea is that this is an image to image translation that we are able to do with the help of this pix to pix paper. And what we are going to do is, we're going to have a black and white image of the galaxy and then convert it into some kind of realistic colorful images. And one more thing, if I can show it to you, see, there is a database of 50,000 shoe pictures. So to train again, you should have a diverse data set, plus there should be a lot of samples. As compared to if you know about the astronomical data set, it's very scarce to get this kind of data. So it's not possible to have 50,000 of such images. We're having less set of images, but still we'll try to see how much amount of great outputs we produce. The aim of this program is help you understand that this is kind of thing you are able to do it if you're having good enough of data set, right? So if you're able to have a data set, implement the same things I'm teaching you over here, and I'm sure you're going to get amazing, wonderful results. Okay, let's try out some of the examples over here. Okay, I'll just clear this and try to create my own cat over here. Okay, obviously my edges are not that good, but let me try to draw the face of the cat. It looks more like a skull though. Meow. And maybe some ears. A devilish cat maybe. Let's see what it does. I see kind of a cat, right? You can see that it's following the edges, the shape of the face is clearly visible, right? The eyes and the kind of mouth, even the mustaches, if you can see, it's visible. The first time, in your case, once you're going to click on process, it's going to take some time to load the model. But I've already done that thing, so that's why once it's going to load it, you can get the outputs as soon as possible. Okay, let me try to draw some kind of body. Maybe now let me try to also have mustache. A weird cat that you must have possibly seen. You can see it's able to capture some detailings, right? So that's about edges to cats. All right. Like this, we're having another example. Well, I'll just clear all these things. I can draw like what we had. For example, yeah, this kind of things we can have. We can have an entrance. We can have multiple doors. We can have multiple windows. Then we can have balconies, so on and so forth. Let's try to have one for our case. Yeah, I'm going to clear it. Let's try to have an entrance over here, and let's try to have a bigger entrance. Okay. Then let's try to have one door over here. That's going to be like this. What are the other things we can have? Let's see. Wall. Let's try to have a wall. I'm not able to say it because the color is same, so I'll just undo, 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 undo. Okay. I'll again have my door. Oops, it's not looking good. So here is my door, and then maybe I'll just try to have a balcony over here. Balcony 1, balcony 2, and a balcony 3. And let's say we are having a window. That's my window 1, window 2, then 3, 4, and a bigger window over here 5. Let's see what else I can add. I guess let's just try to have the process. See, it's downloading the model because I did not try it before. So it's going to take time to download it. Meanwhile, let me show you some other example. So this is to get shoes from edges. I guess until this is going to run, it's not going to allow me to run this. So over here, you just give edges of some kind of shoes, sandals, boots, whatever you want, and it's going to create a realistic looking output. Okay. And every time you will see that it's approximately 50,000 images. So the importance of the data set, the number of samples in the data plays an important role over here to get a real looking outputs. Okay. So over here, this is the input and this is the kind of output for the edges to handbags. You can try it out by yourself, right? It's important that you know that the models were trained and exported with the pix2pix file, and they followed some of the ways through which they got this done. But yeah, now you can see that, see, this is the entrance we had, this is the door, then there are two balconies on the top. Sorry, yeah, these are the two balconies, each with two windows. Over here also, if you can see, there is a balcony and a window. So this kind of outputs you're able to get, isn't it just great? Let's say what happens if I just have two doors, or let's say four doors. One, two, three, four, and a window in between. Let's try to add a wall over here. Let's see what happens. So kind of a wall you can see on top of the door. There are four doors and a window over here. And one funny thing I would like to show you is we have trained on about 2000 stock cat photographs and edges automatically generated from those photographs. Now it's important that you understand that at times, depending on what kind of inputs you are going to give, it's going to give some weird results. And one of the examples that they've given over here, if I can show it to you, is this one. Just look at that eye. Look at the shape, multiple eyes. So yeah, if you are going to give some weird input, similar outputs you can expect. All right, so this was the two examples. Now, apart from that, the third link is about multiple different examples. There are 18 such examples that you can try about and look into it. Okay, so this is about generating examples for image data sets. These are to generate, if you know about this, guys, this is from the MNIST data set, where you're having different numbers and you're trying to produce this kind of numbers automatically and randomly. Okay, and over here is the face data set. And yeah, over here we are having another data sets. And this is about the one that we had talked about, right? The style to gain. And if I can see if this was from style to gain or something else, it's from the progressive growing of gains for improved quality, stability, and variation. So this is really good looking outputs, as you can see. And this is the evolution from 2014. This is the kind of outputs you were able to get. This is the first time. Okay, this is the first time. I guess their person name was Ian Goodfellow, who had got this idea of the GAN. Okay, and the way that, just think about it, uh, that he came up with the whole idea of the GAN, and it literally disrupted the whole field of computer vision with deep learning. Even the person who created CNN, the father of CNN, was highly impressed and said that in a decade, this kind of work was not there. This is for the first time. Even he was impressed, right? But you can see a lot of different kind of examples are there. And if I talk about image to image translation, that's what we're going to focus on. Okay, and here the some of the examples that they have given to you is from day, you can convert it to a evening time. So this is the images that you are having in your real data set. And this is the output that you have produced with the help of GAN. Okay, then edges to actual image. So this is exactly what I told you in the previous example. Over here, you give this input of the image, and that's the kind of reconstructed output that we are able to get. Then over here, you give the image of the street view, and it's going to convert it to a Google Map kind of thing, right? So all these kind of examples are there. We are going to follow one where we are going to give a black and white image as an input, and then it's going to produce respective colorful outputs, right? So yes, these were some of the examples that I really wanted to share with you guys, that this is the kind of work that we are going to achieve in this program. So I hope you all are excited, just like I am, to show you how these things work. So this generative adversarial networks consists of two different neural networks. And then this neural networks fights with each other or competes with each other to get the optimal results of GAN. And by the way, from the name itself, it suggests that the networks, the two neural networks, are trained with the help of adversarial training, where both of these networks are going to compete with each other, and therefore the name adversarial networks. They're going to compete with each other to produce some output, and therefore generative adversarial networks. So I hope that the name is having some sense, what it means. It is going to have two neural networks, it's going to compete with each other to generate some output. Now, what are these two neural networks? They are generator and the discriminator. These are the two neural networks which competes with each other to produce the output. Now let me explain both of them step by step. So if I first talk about the generator part, it is responsible to create the fake data which should look very similar to the real data. So if you remember, I gave you an example in the previous video about this person does not exist. Every time you run that website, you're going to get a person who does not really exist. So in reality, we are having the features of the humans to produce this output by using those features was not exactly the same human beings that we are having in our training data set. So that's the job of a generator that produce a fake output based on what it has learned during the training purpose. Now, if you remember from our very first video of understanding the flowchart of the generative models, we had two of them: the explicit density and the implicit density. And in the implicit density, I had given you an example that there is a jar, okay, the magical jar, where you uh, just put your hand inside it and you get the cookie that is ready, but you don't really know what are the ingredients being used. It's just ready for you without knowing anything. Now, that's exactly what is going on over here. You just show them the images of different people, and once the training is successfully completed, you get the outputs that's going to give you a person, but you don't really know how exactly it's doing it. It's still able to do it. So the idea of generator, if I talk about in the statistical terms, is there are two different probability distributions. One that is for the real data and one that has been generated by the generator. And the goal of this GAN training is to make this probability distribution of the fake data very similar to what we are having for the probability distribution for the real data. If we are able to get there, that's where we say that we have trained our GAN successfully. So that was the role of the generator in the whole generative adversarial networks. Now let's talk about the second network. You might be wondering that, hey Rohan, if we are already getting the outputs from the generator, then why do we even need the discriminator? Well, without discriminator, generator is nothing. It's just like how two siblings are there. They usually fight, but without each other, they cannot progress in their life as compared to how progressive they can be if they are with each other. It's very similar to like that. Generator cannot perform well if discriminator is not there. So the idea of the discriminator over here is it assesses the authenticity of the fake data coming from the generator. How? By distinguishing it from the real data. So the task of the discriminator over here is to identify the real image as real image and the fake image as fake image. Again, you might be confused, right? What's the whole game over here? Why do we even want to do that? Well, the fake data that we are giving to the discriminator is coming from the generator. So if my discriminator is telling that my fake data from the generator is actually real, it means that your generator is able to produce good results. It's going to get some kind of a feedback from the discriminator that, hey, dude, you're performing well. And the task of the generator is to fool the discriminator. That, what, if I give you a fake, you should still classify it as real. So generator is trying to fool it, but the task of discriminator is not actually to help generator. Rather, if it's a fake, it's going to tell it it's fake. But the optimal level of GAN training would be when both of them are learning parallelly. In the initial state, neither discriminator or generator are powerful. Slowly with time, both of them are going to improve. Where discriminator, if it says that, if it's correctly identifying that fake is fake, real is real, that kind of feedback is going to tell generator that you need to improve further. And let's say that generator is able to successfully fool the discriminator, and for a lot of epochs in the training, this is happening that your generator is successfully fooling your discriminator. That's where we know that generator is able to produce the outputs that is very similar to the real looking data. So that's the overall idea of how GAN works. And by the end of this module, as I promise, you will have a lot of better understanding as compared to what you are having right now. So no need to worry about it. Just know that this is just the beginning. All right. And then I'm having some of the memes to share it with you. When you are training a GAN, I am playing both sides so that I always come out on top. That's exactly what's happening with GAN. Then this is what a discriminator is going to look like. Is it real? Is it fake? Is it real? Is it fake? It's always in confusion, right? Then comes our final slide over here for this module. I mean, for this video. That is, it belongs to the unsupervised machine learning. The simple GANs belongs to the unsupervised machine learning. Where unlike in the supervised machine learning, over here, we don't really have outputs and inputs. There is one data set that we show it to the GAN model, and GAN models are going to produce similar kind of outputs. So there is nothing like input output. There is only one data. We don't split it from that data that this is input, this is output. It's not like that. We pass all the data in a batches, and we ask generator to produce this kind of fake batches. Then it goes to the discriminator. Discriminator is going to give some outputs, and that feedback is going to go to the generator. So overall, it's an unsupervised machine learning where you don't really need to give the targets or the outputs like what you give in the supervised learning. And yeah, model simply improves with time through the adversarial training. Sometimes generator is going to be powerful, sometimes discriminator is going to be powerful, and hand in hand, they go ahead in the progressive direction. If even one is way too powerful as compared to the other, then the problems are going to be there. Okay. And yeah, there are a lot of problems that we are going to talk about in one of the upcoming videos of this module. But yes, there are some kind of challenges with the GANs. But to understand that, we need to stay till the very end of this module. So that's the full GAN architecture that you are having in front of you. So what is the first step? The first step is to pass a random input of some shape. Let's say we are having in one row 100 samples, and all of them are random values. So what's going to happen? We are going to use those 100 random values to produce an output that's going to be very similar to the real data. And who is responsible to get it done? That's the generator, our boy over here. So this generator is going to get the random inputs. Initially, it's not going to give you a really good output, but yeah, you get some kind of reasonable output over here. Then for the discriminator, you pass both of this data as an input to the discriminator. Okay, you pass the generated data that you got from the generator along with your real data to the discriminator. And what's the task of this discriminator? It has to correctly identify the generated data as fake and the real data as real. Now, once we are having these outputs from the discriminator for both of them, okay, for both of them, you'll have two different outputs, one for the fake image set and one for the real image set. So, what do? You use those outputs to send feedback for your generator as well as the discriminator. So, discriminator is going to use both the outputs to update itself. And for the generator part, it's just going to use the outputs that it has got from the generated data. And if you think about it, the architecture of the discriminator is nothing but a binary classification model. So you're going to train a neural network that's going to classify the output as either true or false. That's it. That's what a discriminator is. And if you're having a little bit idea of how this works, in binary classification in neural network, the activation that we use in the final layer is going to be sigmoid, which gives you the probability in between 0 to 1. So now what's going to happen is that once discriminator is giving you that kind of probabilities, so what is the probability of discriminator predicting this generated data as generated data? You get that probability, send whatever is the output to the generator, it's going to use it to update itself. If discriminator is able to understand that this is fake data, then generator is going to update itself in a way that in the next epoch it's still again going to try to fool it. If it's able to fool it, then discriminator itself is going to try to identify in the next epoch generated data as the fake data. So parallelly, this kind of training is going to go ahead. Okay, it's going to go ahead, and finally, we are going to have a balanced state where generator is able to produce real looking outputs. Let us quickly revise what we have studied. The first step is to get some random vector to the generator. It's going to generate some kind of image. Now that image and the real data, or the image from the real data, both of them are going to go to the discriminator, and we calculate the loss from it. And the output of this discriminator and the loss that we have used, we use it to update our discriminator and the generator model through the back propagation. And that's why this training symbol is given to you. That whatever loss that you generate, get the partial derivative of loss with respect to your respective model parameters. Once you have that, you run an optimizer on top of that to update the model parameters in a hope that both of them are going to update itself or upgrade itself. And the basic ideas I've mentioned even in my previous videos is the aim is to get generator produce real looking outputs. Initially, it's not going to do it, but with time, it's going to do it by getting the feedback from the discriminator continuously after every epoch. So that was about a complete GAN architecture. The real important part that you have to keep in mind is that how generator is going to give an output and how discriminator is going to give an output. Generator is going to be a model that's going to, from the random vector, get a picture. So how is it going to do it? I'll tell you once we are going to build a network. We basically use upsampling technique. Okay, from a random sample, we convert it into a three-dimensional shape, and then we keep on upsampling it until we get the shape of the image as we have in the real data. But then we pass both of them to the discriminator, and the job of the discriminator is what? To give the outputs for both of them as a sigmoid probability in between 0 to 1. Then the loss is calculated, then the gradients with respect to the trainable variables is calculated, and then we update both of them by applying the optimizer. So that's about the GAN architecture over here, guys. Now just trust me when I'm saying this is one of the very difficult concept to understand. Okay, it's not that difficult, but for the beginners, this is one concept where they usually ignore it and just move on. But this is my attempt to make sure that you're understanding the complete idea about the cost function that we use in the GAN. Okay? Just in case we are still having doubts at the end of this video, please feel free to connect to us and we'll make sure to reply to all of your doubts. Okay, you can reach out to us through Udemy platform, through Instagram, LinkedIn, WhatsApp, whatever suits you the best. Okay, so talking about the loss function or the cost function, because we are having two different neural networks in our GAN, we are also going to have its respective loss functions. So because we are having two models, we'll also have two loss functions, one for the discriminator and another for the generator. For the discriminator, it is responsible to correctly predict real as real and fake as fake. For generator, it's responsible to fool the discriminator by making it predict the fake image generated by the generator as a real image. So that's something that we have already covered from our previous video, but just a quick recap. And that's how the loss function is going to look like that we are going to use for the training part. Just a heads up over here that there are a lot of different types of cost functions that you will always see about the GAN. It's just the same thing represented in different ways. You can use the one that is going to help you understand it the best. According to me, this is going to be helping me the best, and that's why I've chosen it, because even in my implementation I'm going to use the exactly the same thing with the help of binary cross entropy. I'll talk about it later on. So over here, this is going to be working like a minimax game. Okay, where the idea is that this objective function, one wants to minimize it and one wants to maximize it. Okay, don't really get confused by like looking into this weird kind of equation. It's not that weird. Okay, trust me, guys. Let's understand both of them one by one. For the discriminator loss, what's important? We want our discriminator to correctly predict real as real and fake as fake. Over here, this d of x basically means it's the output from the discriminator of probability in between 0 to 1 if the input is a real image. This basically means the output of the discriminator again in between 0 to 1 for the inputs of generated image, that is the fake image. That's one thing you need to understand. And what we want that if it's a real image, this should be predicted as 1. If this is a fake image that we have used, we want to have this kind of probabilities as close as possible to 0. This as close as possible to 1. This as close as possible to 0. So according to this, we are going to understand that how we want to maximize this objective. So I've given a summary for that exactly the same thing. For this d of x, it's the probability predicted by the discriminator on this real inputs. We want d of x to be as close as possible to 1, as then we can say that discriminator is correctly predicting real data as real data. If the probability of this discriminator on the real data is going to be closer to 1, obviously we know that it's performing well for the real set at least. And similarly for the fake images, over here, this represents probability of predicted image, the probability predicted by the discriminator on the fake samples. And we want this to be as close as possible to 0, right? We want this probabilities to be as low as possible so that we are correctly identifying, we as in discriminator is correctly identifying this as the fake image. So that was an idea about what we want to get from the discriminator. Now, by having this idea, how do we want to maximize this cost function? Let's try to look about that. So I've gone through the Desmos and I've tried to plot on the y-axis, we are having the log of dx. Okay. On the y-axis, we are having log of dx. On the x-axis, we are having the inputs of dx. And because dx is the probability, it's going to be in between 0 to 1. So how the log graphs look like? If you're aware about it, then it starts from the negative infinity, crosses the x-axis at 1, and then keeps on going up like this. So if I restrict the inputs in between 0 to 1 because of our probability nature of the dx, we can see that if we want this dx to be as close as 1, we want to maximize this loss as much as possible. If we are able to fully maximize it, the output will be getting to 1. And similarly, for the second term that we are having over here, we know that we want to get this term as close as possible to 0. And if I plot on the x-axis the discriminator output for the generated images, and on the y-axis log of 1 minus that, and that's the kind of graph that we are going to get. And this time we want this d of g of z to be as close as possible to 0. So if we are able to go to 0, we are going to say that we are trying to maximize this objective. So I hope that you're getting an idea that why discriminator wants to maximize this objective. Well, I've talked about that for like, what is this term and what is this term. Now, what is this E and what is given in the subscript of it? Well, this is called as expectation. Okay, you are going to calculate the mean for all the samples in a batch or maybe in your training data. So what's going to happen? You're going to calculate the mean. Over here, this is for the real data. This is for the latent vector or the random values that you had created to generate the fake image, and then we used it to get this kind of output for the log, the loss actually. So Z is indicating that we are going to have this expectation for this fake data or the fake outputs generated by the discriminator. This is for the real outputs generated by the discriminator on the real images. E basically means the expectation, and we are going to use mean for that. So that was about the complete idea for the discriminator. Now let's talk about generator. For the generator, if you can see in both the terms over here, G is not present. I can write the same formula even for here. There is no problem, because when I'm going to calculate my gradients with respect to the generator, I know that in this term, because generator is not involved, so it's irrespective of my generator. If I do partial derivative of this term with respect to generator, I know that it's going to be 0. So I can simply ignore it. And if I'm ignoring it, I am just left with the right hand side part. Okay. And over here, if you remember, the aim of the generator is to fool the discriminator by making discriminator predict fake as real, right? And the idea is that we want d of g of z, even though we are having a fake input, we want this term to be as close as possible to 1. If that is what is happening, it means that discriminator is not able to correctly identify fake as fake. But then we are having this idea that your generator is able to produce results which are very similar to the real one, right? So the probability predicted by the discriminator on the fake inputs, we want this term to be as close as 1. And that's where we are going to fool our discriminator. And with this logic, if I show you the graph, what do I want? I want this to be as close as possible to 1. And on the x-axis, you are again having this term. And on the y-axis, you are having log of 1 minus that term. You can see that to get to the 1, we need to minimize this objective as much as possible. That's where we are going to have this value going towards 1. Again, the expectation, and because we are using the fake inputs, we are dealing with the Z distribution, the random distribution, which we are trying to approximate it to the real distribution with the help of GAN training. So I hope that the minimizing of this objective is clearly understandable by knowing the fact that we want this term to be as close as possible to 1. In the previous slide, I told you that this has to be closer to 0. Why? Okay, sorry, not this slide, but this slide. I told you that this term has to be as close as possible to 0. Why? Because the aim of the discriminator is to produce the fake outputs as 0. Okay, we want these values as close as possible to 0 because these are fake, and I want my discriminator to predict this as a fake, which is only possible if the probability is closer to 0. As opposed to that, in my uh, generator part, I want to fool the discriminator, and therefore I want my discriminator to predict this as 1. Whatever it predicts, the information from this loss is going to be fed back to my generator. Okay. And if you notice, in both of these loss functions, the outputs are dependent completely on the discriminator's output. It's going to have two outputs, one for the real set, one for the fake set. Okay. And accordingly, it's going to send the feedbacks not only to the discriminator but also to the generator part. Okay. And here is the summary notes that you need to take for this loss function. The aim of the discriminator loss is to maximize it. And it's going to be done by combining two losses, one for the real outputs and one for the fake outputs. What are these real outputs and the fake outputs? These are the outputs that we have predicted by the discriminator. So the probability of the discriminator on real images will be real outputs. Probability of the discriminator on the fake inputs will be the fake outputs. So for the real outputs, we want to have a discriminator loss. And even for the fake outputs, we want to have a discriminator loss. This is for the real part. This is for the fake part. We add them together, we get a discriminator loss. For the generator, we are going to use only the fake outputs, right? But what's happening? These fake outputs are again the outputs from the discriminator itself, right? The outputs are again from the discriminator itself. So discriminator is helping not only like give feedback to the discriminator, but also give feedback to the generator. It's an important thing that you are learning over here, right? And I've mentioned about what are the real outputs and the fake outputs in this line, that the real and the fake outputs are the outputs by the discriminator model on the real and fake inputs respectively. So generator is updated based on the feedback it received from the discriminator. Okay, that's an important thing that you're learning over here. That generator is updated based on the feedback it received from the discriminator. If discriminator is telling that it's a fake data, then generator tries to improve itself and tries in the next epoch that discriminator tells this fake image as real. So that's that adversarial nature. I hope you are able to understand it. Let me quickly once again go through all the slides of this loss functions to help you understand it in a better way. There are two losses, one from the discriminator side, one from the generator side. For the discriminator, we want to maximize it. We want the real data to be treated as 1. We want this to be treated as 0 or closer to ones and zeros. So if this is going to be closer to 1, we can see that according to the graph of the log of the discriminator, we want to maximize this. Similarly, we want this to be closest possible to 0. We still want to maximize this. And for the generator part, we want this to be closest possible to 1 to fool the discriminator. And that is possible by minimizing this objective. So yes, that's the idea of this minimax game that we are talking about. So yes, that was about the most crucial concept that I really had to explain, and I hope that I did a justice to explain this idea of the cost function that we use for the GANs. Now, before we actually talk about the balance training part, let me first help you understand that what is that exact cost function that we are going to use while building our GAN. Okay, how will we get these things over there? How will we get these discriminators and all these things? Well, if you have ever worked on binary classification task with the help of a neural network or even with the help of, let's say, logistic regression, you must have come across this kind of cost function called as binary cross entropy, which works exactly in the same way. You are having a log loss over there where you give log for the real values and the log for the duplicate, or I should say the fake values, right? Log of the probabilities for real outputs and log of the probabilities for the fake outputs. So over here, we are having the same idea. We are also having the mean. So yeah, that's exactly going to be the binary cross entropy. By keeping that thing in mind that we're going to compute the cost functions with the help of binary cross entropy, and same goes for the generator, just know that this value will not really hold any significance because it's independent of the generator term. All right. But then if I talk about the balance training part, we can't let either of this discriminator or the generator to overpower the other one. The reason behind this is we want the discriminator and generator to improve together concurrently, parallelly. This is only possible when D performs well in few epochs, then G performs well, and again this kind of cycle will continue. So if my discriminator is performing well for certain epochs, then what I want, if it's performing well, if it is able to identify fake as fake, generator is going to try very hard to fool the discriminator. Once it's at that state, then the generator part is going to be slightly dominating as compared to the discriminator model, where now generator is able to fool the discriminator and discriminator now is not able to classify the fake as fake. So what's going to happen? Now discriminator is going to thrive very hard to get this uh, predictions from the generator part as close as possible to 0. So once again it's trying hard, and if it gets this stage, then yes, the balance will again tip off. Discriminator is going to perform well, generator is going to not perform well. Okay. And this is an example of how a GAN loss outputs are going to look like. Initially, both of them are going to be high. And what's going to happen? It's going to decrease like this. So what's the idea over here, guys? Okay, what's the idea? You can see that initially, obviously, it's trying to get that state, right? It's starting to obtain this for the discriminator, for the generator. That's how it's going. But after certain epochs, okay, this is not 5, 10, 13 epochs. You can see that there are 30,000 epochs for which they have trained. GAN really needs a lot of epochs of training to start getting a good looking outputs. So as you can see that after certain epochs, we have got this kind of a balanced training where there are some kind of ups and downs in both generator and the discriminator. So wherever there is down in either of it, it means it is the time where it's going to learn, right? And then when it's going to go in the upward direction, that's where it means it's performing well, right? Or I should have said the opposite way around. Okay, when the loss is less, whenever the value of the loss is going to be low at that time, it is performing well. Okay, so when it's going to be higher, when the loss is going to be higher, it means it needs to improve itself, right? So it's going to improve, the respective model is going to improve when the losses are going to go in the upward direction. If it's going in the downward direction, it's well and good. One will go down, another will come up. So that's the adversarial nature of the training. And that's the kind of balance we want, starting from the respective values. But later on, like with some kind of fluctuations, we want a balance to be there. And what's going to happen? For the desired epochs, the final outputs would be you take the generator, feed the random latent vector, it's going to give you the output that's going to be very similar to the probability distribution of the real data. So that was the whole concept of the balance training, and the important part you need to focus on is that this balance training will eventually lead to stable training and better convergence of GAN, as you can see. Now, the optimizer that was used in the original paper of GAN was the stochastic gradient descent with momentum. But then, to solve some of the challenges that we have in GAN, a lot of times we have seen that ADAM and RMS props are working great. Okay, so we are going to use ADAM for our project that I'm going to show in the upcoming module. But you can always try different optimizers and see that which is going well with the model and for the data that you're using for your purpose. Okay, we are going to use ADAM, but you can surely try STD with momentum, RMS prop, and other bunch of optimizers. The important thing is that you try with one, try with other, and see out of both of them which one is performing well. And don't forget to tune your hyperparameters over here, okay? Because for different data sets, it's going to be different, okay? The nature of learning is going to be different. So in the previous video, we had talked about the cost function. We are going to use binary cross entropy, and the optimizer is going to be Adam. So let's begin by talking about the training instability, which is the major problem with GANs. And when I'm saying major, all the other problems, somewhere or the other, are related to the training instability. Okay. In one of our previous videos, we talked about the balance training. Well, in theory, it's very easy to talk about this, and for you guys to understand it, it's very easy concept to understand. That if my discriminator is uh, learning, that means my generator is performing well. When my discriminator is performing well, then my generator is going to learn to overpower the discriminator for a time being. So that's how we are going to get this kind of parallel training, where none of them is going to be like my generator is performing so well that my discriminator is not even able to learn. That kind of thing should not be there. And therefore, the balance training that both should go parallelly. Okay, if one is increasing, the other one is going to catch up, because when other one is catching up, the previous model is not improving, because that's the time of the other model to improve. Okay, if my discriminator is improving, my generator won't improve, because if my discriminator is improving, what's going to happen every time it's telling my generator is not producing good results, and my generator is going to try hard. that I need to beat my discriminator. So that parallel training is going to happen, and if discriminator is going above by some percent, then generator must catch up. That's the balance training. And to get that kind of balance training is very difficult to achieve with GANs. And therefore, the first point, GANs can be notoriously difficult to train due to their adversarial nature. What's going to happen in most of the cases is that, let's say my generator is performing well, it will keep on decreasing the loss. But then for my another model, if it's not performing well because my generator is literally overpowered, then what's going to happen? My loss is not going to be better for my discriminator. So this stability is not there in short. If one is going down, one is going to spike up, which says that one is performing well, but the other one is not performing well because of that. And this instability is very easy to face whenever you're dealing with GAN. And in fact, in your next module, I'm going to show you an example of the training instability. Then in the next module to that, I'm going to tell you a way through how you can solve it. Okay. So as I mentioned, the continuous oscillations in loss values leads to the failure in convergence. And by looking at this kind of a loss output, if both of them are going in the balanced way parallelly, that's the balance string, and somehow it's going to reach to the convergence. But let's say if one is going down, the other one was going down, but then suddenly it spiked up. Then again it comes down, then again it spikes up. So that instability is clearly seen in this kind of cost outputs with respect to the epochs. So that's what is mentioned, that to identify this problem, this is one of the way. Alternatively, the other way that you're having is to produce the outputs from the generator directly. Okay, you can take some of the images from the generator and plot it in front of you. You will see a common trait of distorted and noisy images if training was not stable. Okay, you can clearly see it. I'll show you one example, and this is the example that I'm going to take from my upcoming module. Okay, I've taken the outputs from there, and you can see that we are having distorted images. Actually, these are the galaxies that we are having. We are trying to produce images of the galaxies in the center, which could be circular, elliptical, right? And or irregular, whatever kind of shape it is. But you can see that it's taking a lot of noise. It's not giving good results. And this is the output after 1,000 epochs, guys. Okay, after 1,000 epochs, not after 2-3 epochs. So that's the problem. Because of the training instability, we are able to capture it just by looking at this outputs of from the generator. And to solve it, you need to spend a hell lot of time experimenting different things to obtain the balanced training. Some of the things that you can do is that, let's say your generator is performing good and discriminator is not performing good. Or usually the case is opposite, okay, that your discriminator is soon going to perform so good that your generator is not going to improve. So what's going to happen in that case? Your discriminator is learning at a faster rate as compared to your generator. So initially, we are going to have both of them having the same learning rate, okay? But then when this kind of things happen, you try to slow down the learning of the model which is learning at a higher pace. How you do this? By decreasing its learning rate. If you decrease the learning rate, it's going to go to the convergence but in a slower rate. It's going to improve, but it's going to slow down the training at the same time. So if I, let's say if that's the case where my generator is not performing well as compared to my discriminator, I'll try to stop my discriminator. I'll try to slow down the discriminator, not stop, but slow down the discriminator by decreasing its learning rate. The other possibility where, let's say your generator is very overpowered as compared to your discriminator, you can try to check the architecture. It shouldn't be like my discriminator is very shallow and it's not able to understand the features itself so that it can classify it correctly, real as real, fake as fake. So you need to have a good architecture for your discriminator to make sure it is having the capacity to understand all the features coming from the images and then make a decision if it's true or false, right? And do some kind of experiment, add some layers, remove something, and do this kind of different experimentations to get balanced training. Well, the way that we are going to solve this problem is by changing the loss function itself. Okay, and more information I'll I'll give it to you in our third module. But for now, this is the major problem that I really wanted to share. That is the training instability. Now, the second problem is the mode collapse. This is where your generator collapse and it's not able to produce a variety of outputs. Rather, it's producing good outputs, but in a limited range. What does that mean? I gave you the example of that this person does not exist, right? What if I tell you I'm generating a very similar person again? The moment I refresh my site, it's giving me the same person with different kind of slightly different features. So that is mode collapse. My generator has collapsed in a way that it is limiting itself to produce different outputs. Okay. From the large part of the data distribution, it has just captured some parts of it, and because of that, still it's performing well. Okay. It's performing well. But the outputs because of this are going to be limited. The output of the generator, the capability of that will be limited to certain type of traits present in your data distribution. So the first point is that the generator produces limited varieties of outputs, ignoring different parts of the data distributions. And this can be identified again if same or very similar kind of images are generated repeatedly from the generator despite diverse training data. Okay, and again over here, if you can see, in all of them obviously we need to produce galaxy, so it's going to give some kind of bright pixels in the center, but you can see that the nature, like the shape is approximately the same, whereas in the real data set we had variety of different shapes. In some of them we were able to see the spiral arms, in some of them we were able to see the irregular galaxies, in some of them we were able to see the disk of the galaxy. So we had a lot of different features, but it's not able to capture them. So that is what is mode collapse. Again, if you try to solve the stability of the training, this issue can be solved, because again, if you're having a stable training, then my generator is going to have its full capabilities to produce all the range of outputs from its data distribution. Then third problem that we are having with the GAN is of the vanishing gradients. This is going to happen for the discriminator when your discriminator is going to be very powerful. If it's very powerful, that every time it's winning, generator is not able to win, what's going to happen? Generator is not going to get a meaningful feedback of how to improve, because the discriminator dude is just telling it that you cannot improve, dude. I'm going to make sure every time you're going to do any kind of changes, you don't improve. I'll make sure to pull you back down. But when it comes to me, I'll keep on making myself good and good, so that whatever you produce, I'll always defeat you. When this happens, my generator is not able to learn. So what's happening mathematically? If generator is going to slow down its process of learning or just stop in the worst case scenario, that's the reason when the gradients vanishes for the generator part, it is going approximately closer towards zero. And when this happens, we are simply saying that it is not having meaningful feedbacks, and that's what is not able to improve. Hence, again, the training stability plays a very crucial role to not let discriminator to be that good that it doesn't allow a generator to even learn. So yes, these were the three different problems that I really wanted to share it with you guys for the GANs. We are going to come up with a way in our third module of this program. In the second module, I'm like that's the next module. I'm going to help you understand about how to create a GAN model. But then how to solve that problem of stability, or sorry, I should say instability with the GAN. There are a lot of ways. Okay, I'm not going to go and talk about change the learning rate, change the architecture, because it's going to be more time consuming. As compared to that, I will be taking a different version of GAN that's going to be far stable as compared to the normal. Okay, so all these kind of things are going to come up in front of you. So I hope you are very much excited to look into the upcoming modules as well, guys. So that was all about our first module. And I hope that all of you are now comfortable with the idea of the GAN. What are some different generative models? What are the different capabilities of the projects that you can do with different types of GANs? And then what exactly is the traditional GAN? How is it going to look like? What are the loss functions we are going to use, the optimizers, and the balance training, how the balance training should be there in the GAN? And then what are some of the most common problems with the GANs? Now, given that all of these things are there in your mind, it's the right time to go ahead and try to implement this on some problem statement and see how it works in real life. That's what is covered in the next module. So I'll see you over there. Hi everyone. I welcome you all to the second module of this program that's on GANs for astronomy. Now over here, given that you've understood the concept of GANs from the previous module, now it's time to implement all of that with the help of one project in this module. And for that, I have divided this module into 16 different videos, starting from understanding the problem statement, setting up the Kaggle notebook, getting your libraries, analyzing the image that you are having for this data set. Then we are going to prepare the function that is going to help us pre-process the images that are present in our data set and eventually use it to create our dataset pipeline. Then we are going to visualize the data after passing through the dataset pipeline, then build our generator model and the discriminator model, define the losses and the optimizers, and then we're also going to set up the checkpoints. And there is a very important thing with respect to this. It's going to help us make sure that if the training is stopped anytime during the training process, we can resume from the epochs which is saved in the last checkpoint. Right? So it's a very important thing that you go through this. Apart from this, we're also going to create a function that's going to generate and save image after every epoch. And then the function to define our training step, because I told you over here we are going to come up with a custom training loop. That's what we are going to do in the 13th video of module 2. And after that we are going to create a function that's going to use that training step to eventually train our actual GAN model. And once all these kind of functions are created, in the next video we are going to go ahead and train the model. And then finally in the 16th video we are going to get the outputs from the generator and look into the how the outputs are being produced by the generator and discuss the final results and conclude this particular module. So yes, all of this is going to help you understand that how you can set up your any kind of project with respect to a traditional game. So yes, let's get started. So the main idea of this project is to use this ground truth folder, which is containing 5,000 different files, and it's containing this kind of different shapes of galaxy images. And the objective of this problem statement is to pass a random latent vector, the noise vector, to the generator, and we want that generator to generate this type of galaxies from the random numbers. So just like how we had seen that this person does not exist website, over there whenever we are running the website, it is giving us different outputs of human beings, but then that human beings does not exist. So the same kind of task we are trying to achieve over here, that if I'm going to give some randomness as an input, it's going to generate a galaxy that is it's going to be very similar to what you are seeing over here. That's the idea. Okay. And yeah, so let's see how we can go about this throughout this module. I am very much excited to get started with this, and that's exactly what we are going to do by setting up our Kaggle notebook from the next video. So I'll see you over there. So the first step over here is to open a fresh notebook on Kaggle. If you are not aware about this, this is very similar to Google Colab. So what you do is you go to kaggle.com, register yourself over there, and then log in. Once it's ready, you can click on this plus icon and then click on the new notebook. The moment you do these steps, you will be having this kind of a notebook ready in front of you. There will be some kind of codes written over here. You can simply delete it. But then you will be having a notebook just like what you are seeing in front of you right now. So you can just get started by changing the name of the notebook. I'm going to write it as GAN implementation .ipynb. And then I'm also going to give a title to this notebook. I'm going to have a markdown cell I'll delete this one and say that this is generate galaxy images from random numbers using generative, or simple I'll write using GAN, and I'll give a h1 heading and a line break. So that's how it's going to look like. For now, what I'm going to do is I'm going to just skip this like at 150% of the zoom, because if I keep it 125, even though it's looking good, but the font size are a bit small for you guys to see it. And one more thing I'll do is I'll just change this with a center tag so that it's going to appear in the center. Okay, so this is looking good, right? Now, I need to add the data set that I'll be using for this project. And for that, I am having a data set uploaded by Spartificial itself. And over here, I just need high resolution galaxy images out of low and high resolution galaxy images. So for that, we are going to use this particular folder, that is final ground truth, where as you can see that we are having images of galaxies in these photographs. So we need to get an access of this kind of data set on my Kaggle notebook. So how can I do it? I simply need to copy this. I'll click on the arrow on the bottom right, click on add input, and then simply paste that link over here. And I'll need to click on this plus icon now. And then I'm going to cross it. As you can see that my dataset is now available on my Kaggle notebook. Now I just want to connect this notebook to the runtime. So I'll say print test. I'm going to run this code cell. So yeah, my notebook is already started. So yes, that's about setting up my basic notebook. And yeah, I'll just delete this code and I'll have my markdown cell and talk about what we are going to cover as a first step. That would be to import the libraries. And that's what I'm going to do in the next video. So stay tuned for that. So the libraries that I'll be importing over here, to get started with, I'll import numpy as np and import matplotlib.pyplot as plt. So this is for the numerical operation and handling arrays. This is for the visualization part. Now, apart from this, the things that I'll import over here for handling the file is import OS. Then this is for handling of the files. This is for the arrays. This is for the visualization purpose. Now to build a model, for that I'll require TensorFlow. So import TensorFlow as TF. And to get layers, I can also have uh, from TensorFlow.keras, I can import layers. So from TensorFlow.keras, import layers. After this, let's say if I want to read an image, I'm going to use skimage.io for this one. So from skimage.io, I'm going to import imread. So with this, I'll be able to convert my image path into NumPy array. And other than this, one more thing I'll need to import over here is from IPython. I want to import display. And this is going to be useful for me whenever I'm going to display an epoch. In that epoch, I'll be displaying the generated images from the random numbers by my generator. So for every epoch, I'll be showing this and then clearing my output. Again, showing it and clearing my output. So for that, I need to clear the outputs, and that is what I'm going to do it with the help of this display.clear outputs. And you will understand it once I show it to you. And now that we're already talking about displaying the epochs, let me also display the time it took for that epoch to run during the training process. So for that, I'll need to import time module. So I'm going to run this code cell. Again, let me just go ahead and quickly give you an idea. This is for handling the arrays. This is for the visualization part. This is for file handling. This is to get our model. This is to build the model with different layers. This is to read an image, and this is for clearing the outputs in the training process, and time to display the time it took for an epoch to run during the training part. So that was about importing the libraries. Now in the next video, we are going to talk about how we are going to load and prepare the data set. Okay, so that's our step 2. This was our step 1. Now we are going to talk about step 2. That is about load and prepare the data set. So more on this, I'll talk about it in the next video. So stay tuned for that. So whenever we talk about building a dataset pipeline, it is really important that we load any of this image or maybe multiple images and check about some of the properties of the image to understand it in a proper way. Once we understand it, we can go ahead and come up with some kind of dataset pipeline. So later on in the next video, I'm going to talk about how to build a TensorFlow's dataset pipeline by using its API. Right now, let's try to just analyze an image or two and get some idea about it. So for that, I'll need to load one of the image. And for that, let's say I'm choosing the first image. I'm going to copy the path of it. Create an image path is equal to that. I'm just going to paste the path as a string. And then I'm going to use tf.io.read file and give image path as an input. I guess I talked about I'll be using skimage to read the files, but then this is going to give me array, numpy array. But to train this kind of a model with the help of TensorFlow, I'll be using tensors, basically with the help of TF. So this is going to be the read image is equal to this. And then I want to decode this as JPEG because if you notice, the extensions of all of these images are JPEG. So what I'll do is I'll say that image is equal to tf.image.decode JPEG. And then I need to give read image, the image that I read over here basically, and giving that as an input. Along with that, I'm also going to give channels is equal to 3. Okay. And let's check what's going to be the shape of this image. So it's 128 by 128 by 3. Okay, that's the shape. What about the data type? Image.d type. That's going to be uint8. So the range of the data, that is basically the range of the pixels, is in between 0 to 255. You can also check it. For example, if I do tf.reduce max to get the maximum value in the tensor, it is going to be 246. So in between 0 to 255, the range is going to be there. If I do tf.reduce minimum, it cannot be negative. Must be in between 0 to 255 because of uint8. So you can say it's 13. So that's great. We are having a range in between 0 to 255. We can later on convert this in between -1 to 1 while we build our pre-processing pipeline. Why -1 to 1? Because the generator is going to have 10h as that activation function in the final layer. And as you might know, that 10h gives the output in between -1 to 1. And therefore, the output that I'm going to get, I will be having it very similar for the images that I'll be preparing in my data set. So I'll even keep that in between -1 to 1. So this is the kind of idea that I'm having. Now let's just go ahead and check all of these things by giving another image as an example, just to make sure that everything is working fine. I'm just going to copy paste it and comment all of this by selecting all and pressing Control plus / and run this code. So it is 128 by 128 by 3, no problem. uint8, and obviously these two things will be giving the answers in between 0 to 255. Now, if I'm trying to visualize this with the help of matplotlib, plt.imshow with image, and also I'll use plt.show to avoid this kind of output from the imshow. So this is the kind of image that I am having. Now, what if I change this channels to 1? Okay, because we are using matplotlib, so by default it uses viridis as the color map for a single channel image. That's why we can see the combinations of like yellow and violet kind of thing. But let me just go ahead and change the color map to gray, because we had a gray image if we talked about 3 channel image. So you can see that there is no difference between channel 1 and channel 3. So if I again change it to channel 3, and when I do 3 channel images, CMAP does not really get implemented. This is implemented on only a single channel image. So no need to worry about it if you run it. This is the original image. If I change it to a single channel image, it is more or less exactly the same thing. So while building up a model, if you go ahead with 3 channel, you will have more trainable parameters as compared to a single channel. So as such, we don't really have any kind of relation of colors for this project. So I can go ahead with a single channel image as well. So these are the kind of analysis that you need to do before actually coming up with some kind of pre-processing techniques and create your final dataset pipeline. So I hope this was giving you an idea about how to prepare your dataset and what is the pipeline. Okay, what is the pipeline and how to use TensorFlow's dataset API for building a dataset pipeline. I'll show that to you in the next video. So now let's go ahead and create a function to pre-process an image. So for this, what do I need to give as an input? For this, I simply need to pass the path of the image. So over here, what I'll do is I'll just mention the input of this function will be image path and pre-process image. Okay, the spelling is correct. Now, what are the kind of steps I'll be having? The first step is to read the image. The second step is to decode as JPEG with single channel. And the third step is convert the pixel value, or I'll say scale pixel values from 0 to 255 range to -1 to 1 range. So these are the 3 steps that I'm going to have in my pre-process image. And to define this as a function, I need to have def as the keyword over there. So to read the image, what's going to happen? I'm going to have read image is equal to tf dot io dot read file and give the image path over here as the input. Then this is the image file where I'm going to have tf dot image dot decode jpeg, where I'm going to give read image and channels is equal to 1. Just like what we had done in the previous video, that's what I'm following. Now to scale the pixel values to -1 to 1 from 0 to 55, what can we do? So let's just say that we are having pixel values in between 0 to 255. What I'll do is I'll get the middle values. If I do 255 by 2, I'm going to have 127.5. So what I'm going to do is, first of all, I'm going to get the middle value, that is 127.5. Then if I subtract 127.5 from 0, I'll have minus 127.5. So if I divide that minus 127.5 by 127.5, I'll have that output of -1. Right? If I do 0 minus this value divided by the same value, so I'll get -1. And just like that, if I do, because see, what's going to happen is I'm going to have all of my pixel values subtracted by this value. So even this value will be subtracted by this value. This is the maximum value in the array that you can have in the uint8 form. So if I subtract 255 with this 127.5, I'll have 127.5 because this was a middle value. So obviously, if I do 255 minus this, I'll have 127.5. Now, if I divide 127.5 by 127.5, the output will be 1. So from 0 to 255, now I'm going to have the range of -1 to 1. And that's what I need to have over here. And I'm going to implement this with the help of, first of all, I'll just cast my pixel values to float 32. What have I done? I have first casted my values of pixels in the image to float 32 for efficient computation. So I'm not changing the pixel values, just changing the data type from uint8 to float 32. And then after this, what I'm going to do is I'm going to center the values around 127.5 and then also divide this by 127.5. And what is this? This is the scaled output that we are looking for. So scaled image is equal to this. And I'm going to return this scaled image as the output. So we are done with the first step, done with the second step, and we are done with the third step as well. And then if I run this code, and let's say if we try to create image sample by passing any image through this function preprocess image, and we are having one image path already ready right over here. So I'll just give that as an input and check image sample with the help of tf dot reduce minimum. As we can see that the values are now negative and it's not going below -1. And similarly, I can check for tf dot reduce maximum for image sample. You can see that it's not going beyond 1. So that's exactly what we are looking for. Check if the pre-process image function is working fine. So what have we done? We have tried to understand that what kind of pre-process image function is going to contain on the basis of the analysis that we did previously. And then we decided these 3 steps. And finally, we have tested this function that it's working fine. Now, in the next video, let's use this pre-process image function and create the dataset with the help of TF dataset API. So stay tuned for that. I'll see you in the next video. So there are a lot of different ways through which you can get started by creating your TensorFlow's dataset. The one that I'm going to use over here is on the fly, I'll be getting the data and then do the pre-processing and all that kind of stuff as you will see in the pipeline. So the way that I'm going to work with this is I'm going to have tf.data.dataset. So I'm using my dataset API of TensorFlow to create that dataset. So to begin with, I'm going to have list files of that TensorFlow's dataset, and then it takes a directory with the pattern of the file that is present inside that directory to have all of the images loaded over here. So for that, I'll have the path of this ground truth folder, and I want all the images inside this folder that is having JPEG extension. So that's the kind of pattern that I have given over here. And maybe I'll just call it as list dataset and run this. The moment I do this, I can simply go ahead and try to check, let's say for example, that how many, like what is the kind of output that we have produced with this. So for that, what I'll do is I have list ts.take 5 and I'll loop through this. For item in this, I want to print item and then close this up. So as you can see that that's how it's going to look like. Just to make it even more neat, I can just convert this to numpy and then run it. As you can see that these are nothing but the file paths that we are having in the dataset. Now on all of them, I'm going to implement my pre-processing. So how can I do this? I can accomplish this in certain steps. The first step will be to map pre-process function to all these file paths. That's the first step I'll be doing to create my dataset. What will be the second step? I'll try to shuffle the dataset just in case to break any kind of patterns. So shuffle the dataset. After that, I'll cache the data to save time. So what's going to happen is that in the memory, you're going to cache your pre-processed shuffle dataset so that during the training time, it's not going to take a lot of time to load the image, pre-process it, and then shuffle it. You are already caching it into your memory. So from that, it's going to directly pick it up. So it's going to save a lot of time. So that's the third step that we are having over here. After that, you can go ahead and create the batch of the dataset. Let's say you want to use 128 as the batch size, 64 as the batch size. Whatever number that you can come up with, you can go ahead with that. So create batches of dataset. And on top of this, and on top of this, what we use is called as prefetch. Okay? What's going to happen with the help of prefetch? Prefetch is going to help for overall improvement of the performance by preparing the data in the background while the model is training. So what does that actually mean? Let me just say that prefetch the data set. So if I just have to type it over here, keeps the data ready before the previous epoch is completed. So before, let's say I'm running my current epoch, that's my epoch 2. So during the process of this training of epoch 2, if I'm using prefetch, so I'm already fetching my data set during the training of epoch 2 or any kind of epoch for that matter. So for the next epoch, my data set is already ready. The batch of the data set that I want to train is already ready. So again, we are trying to save the time. And again, we are going to use something called as auto tune in the prefetch. For what? For faster processing. And basically, when I use tf.data.autotune, it's going to be very much efficient because it's going to use all the available cores over here. All right. So I can go ahead and fill this dataset pipeline and say that my data set is equal to list ds dot map, and I'm going to call pre-process. What was the name? I'll just copy paste it. The name of the function is what I want to give. Along with that, there is something called as num parallel calls. Okay. So the num parallel calls is where I can have my auto tune. So I'll just go ahead and see if I can find one example over here. See, from tensor slice is also one of the way through which you can load the data if list files is not what you want to do. That is basically mostly useful for the smaller data set. If you're having large data set, you can go ahead with the list files, the one that we used over here. Let me check if they have given some example for the num parallel calls over here. Or else I'll show that to you on the documentation tf.data.dataset. I'm going to open this or maybe this one, close this, and I'm looking for the map. So Control F, map is what I'm looking forward to. So this one. This is actually the official documentation of TensorFlow. So num parallel calls. Let's see if they've explained it somewhere over here. Mm, let me just directly search for this, just in case if they mentioned about this anywhere previously. Yes, performance can often be improved by setting num parallel cells so that map will use multiple threads to process elements, just like I told you, right? All the available cores it's going to use in order to improve the performance. So I'm just going to use tf.data.autotune for that. This is what I was talking about. So I'll copy this, close this, and paste it over here. For the second input that we had, that is num parallel calls. How did I get this mini documentation? By pressing shift plus tab. So num parallel calls is equal to this. Well, I'm really poor with my spelling, so I just cross check my spellings. Num parallel calls, and yeah, by default it uses none. Okay, that's what I'm going to have over here. After that, I'm going to use data set is equal to dataset dot shuffle, and now I need to give some kind of buffer size. And to give some kind of buffer size over here, it basically means that, let's say for example, I'm having 5,000 images in total. If I give a buffer size of 1,000, it's going to take the 1,000 images from the dataset and randomly place it in the dataset. And then if you want to reproduce this kind of shuffling of the data, you can set some seed value. Let's say I'm using 42 as the seed value. If you want to, let's say, rearrange all of your data set, you can give 5,000 over here as well. But over here, I'll be just giving 1,000. Then I'm going to apply caching. So data set is equal to dataset dot cache. Itself, it's going to cache it. I don't really need to give any kind of input. It's going to use this dataset and cache it into the memory for saving our time. After that, I'm going to go ahead and create the batch. Okay. So dataset dot batch. I need to provide the batch size. Okay. So now you can think of, like, what kind of batch size you would like to use over here. It's completely your call, because however you're going to change it and see that, like, what kind of batch size is working well with the implementation that you are looking forward to. Okay. So every time it could be a different value. So just make sure that you are having an idea of the batch size that you will be using for your any kind of uh, pre-processing or training or anywhere, right? So for in our case, we're going to use it for some training purposes for this data set. So I'm going to prepare my data set with, let's say, a batch of 64. You can also go ahead with 128, right? We can change these numbers according to our will. So I'm going to keep my batch as 64, batch size as 64. And then lastly, data set that I'm preparing over here is dataset dot prefetch, where I just need to give, okay, in the prefetch, what do I need to give? I just need to mention again about the tf.data.autotune. Again, what's the reason behind that, guys? What's the reason behind tf data autotune? Just for the efficient training. Okay, I want to use all the available CPU cores so that I'm having faster training altogether. Okay, so only that much, that's what you need to keep in mind. So tf.data data tune auto tune, sorry, auto tune, just like what we did in the previous step as well. I'm exactly having it over here. I'm going to run this code cell and just check that everything is working fine. So yes, that's what we have done over here, and hopefully it's going to work well. And just to check if it's working fine or not, what I'm going to do is I'm going to have my data set and run this. So that's how it's going to look like. What if I do dot take one? And let's do one thing. I'll just create a new video for this. I don't really want to make this video too long and continue explaining about how to actually get files from this dataset as a batch, okay, by using next and iter functions on the dataset. Okay, so to give you a proper idea. And yeah, that's about getting an idea about how to create a dataset pipeline by using TensorFlow's dataset API. To build the dataset object, we have used list files. Then we applied our pre-processing on all of the images that we are having in the list ts, shuffled with the buffer size of 1000. And to reproduce these images every time, I'm fixing the SID value to 42 for the random generator, caching this into my memory, providing a batch size of 64. You can later on change this to any value. Then prefetch to load my data before my previous epoch is completed. So yeah, that's about this video. I'll see you in the next video where we'll be talking much more about how to actually get data set, how to actually read the data and visualize it by using this data set. So stay tuned for that. So now if I run this code cell, this is basically going to give me one batch. So because we have created a batch of 64 images, so that's why you're having 64 images. All of them are of shape 128 by 128 by 1. And if you also want to do the exactly the same thing with the help of dataset.take, I'll need to use a for loop to get this data out of it. But it's this one and the same thing that we are doing in different ways in Python. So I just call it as a batch, and then sample image is equal to, I'll take one of the first samples that I'm having out of 64 and then take that sample image dot shape. So it's giving me 128 by 128 by 1, right? I can exit do the same thing with the help of for loop as well. So let me try to go ahead and do one thing. Okay. I'll maybe take a batch by using a take option and then print the shape of it. And let's see how is it going to look like. So for batch in dataset dot take one, print batch dot shape. Okay, the moment it's going to run this, it's going to print 64 by 128 by 128 by 1. So I hope you're getting a proper idea of how to get an idea about what are the things present inside this data set. Now let's go ahead and try to visualize this. So the way that I'm going to visualize this is I'm going to create a subplot of a 3 by 3. Okay, and in short, there are 9 images in total. Okay, so 9 images I want to show from that batch that I have created. Okay, which batch? The batch that I have just created over here. So if I do a batch, you can see that we are having this values, and all of the values are in between -1 to 1. So I need to again change this to 0 to 255 so that we can see it. So I can do that by just multiplying this by 127.5 plus 127.5. And now you can see that the values are indeed in between 0 to 255, right? So now how can I go ahead and visualize 9 images over here with the help of subplot? So for I in range of 9, where I is going to go from 0 to 8, I need to create a subplot of 3 cross 3 cross I plus 1. Why I plus 1? Because I'm going to start from 0. Or else I could have also done like I plus 1 over here so that it starts from uh, sorry, the way I should have written this is 1 comma 10. So in that case, I don't even need to do I plus 1 because now I will go from 1 to 9. Either you go with this or you go with this idea. Both are correct because I want to have the values over here that goes from 1 to 9. And that's what you can play around and come up with. I'm going to do plg.imshow and I want to show the image from the batch. Okay. So batch of 0 for the first iteration. Then for the second iteration, it's going to be batch of 1, then batch of 2. Like that, it's going to run for 9 times, and therefore I'll be getting 9 different images. So in my first index, I'll be plotting batch 0 image. On the second index, I'll be having batch 1 image, right? So on and so forth until I reach up to 9 images. And then I cannot forget to convert these values to the original one as we had previously. And I'll use my color map is equal to gray and do plt dot show at the end and run this code. I'll maybe turn off the axis, plt dot axis off, and I'll also maybe have some kind of a shape, plt dot figure, and fig size is equal to, let's say 12 comma 12. Oh, I need to give this as a tuple. Great. So these are the kind of images that we are having in our data set. Okay. What will happen if I don't do this? Still, there is no problem. Okay, still you are able to visualize the images. There is no as such problem. Okay, I'll do one more time. It's exactly the same thing that you're getting over here. And if I remove this, still you are able to see this. I guess this might be the reason because if I check my batch 0 and then if I check batch 1, these values are currently in between -1 to 1, right? So if I do plt.imshow with gray is equal to, oh sorry, cmap is equal to gray, I can see the image like this. And if I do into 127.5 plus 127.5, then also I'm able to see the image. So I guess the way this IM show works with -1 to 1 is also fine because it's able to display the image. I was under that idea that we need to convert it back to 0 to 55 to again visualize the image in a proper way. But yes, I guess for the single channel image, that's not the case. And yeah, that's what we have experimented. And see, that's how we exactly go ahead and learn. And maybe, to be honest, in the past, I might have come to this. But let's say because out of the lack of practice of dealing with the exactly the same kind of things again, again in different projects, this kind of things is completely okay. Okay. So you never have to feel like, oh my God, I forgot this thing. I need to do research about it. It's completely fine. Okay. Always keep that in mind. So yeah, this is the kind of outputs that we have got. That these are the samples in our actual data set. Like this, there are 64 different images in one single batch. Like that, you have prepared images to store 5,000 images. So if I go ahead and print the value of 5,000 by 64, it's going to be 78 approximately, right? So I'm going to create 78 batches. If I do 78 batches, I'll be missing out onto some data. For example, if I have 78 batches and each of 64 batch size, I'll just be having 4992 images for the training part. So to get all the images that I can fit into the data set, I'll be using 79. Some of the places will be empty in this batch because 56 are the extra things that will be passing without any kind of images, but that's fine. We won't be losing on any images. But to be honest, 5,000 is a really great number for this kind of data set, because you can see that some of the features are very similar to, like, a lot of images. You can see that this image, and this image is pretty much very similar, right? So for that purpose, we can also have 78. Okay, that does not really matter. Just trying to help you that how many batches we can create for this data set. All right. So that was about preparing your data set using TensorFlow's dataset API and visualizing the data that we have prepared over here. Now, from the next video, we're going to talk about how we can build the models. So stay tuned for that. So now that we are done with our first and the second step, now it's time to build the model. And I'm going to start with the generator model. So the whole goal of the generator model is to generate the image very similar to what we are seeing over here. Okay, from random values. So I'm going to choose 500 random values. I can also choose 100 random values. We can just do experiment with, like, how by choosing different size of the random values, how it's impacting the final output. But for now, I'm going to go ahead with 500. And to be honest, this kind of image where we are having very sharp details of, like, galaxies, this kind of image in this data set is less as compared to this kind of images which are very far, and therefore from Earth, if we are capturing this, we won't be able to see a lot of details as what we are seeing over here. So this kind of data, because it will be less in quantity as compared to this kind of data, as you can see over here, we won't be able to, I guess, produce a lot of images that are going to look very much like this. But most of the images will be able to capture this kind of feature, this kind of feature, this, so on and so forth. Okay. But yeah, I'm going to talk about that a little while later once we start generating some kind of outputs. But that's the end goal, that from the random numbers, we are going to produce this kind of outputs. So for that, we need generator model, and it's going to have this kind of an architecture that I've directly taken from the actual GAN implementation, where we are having some inputs. I'm going to pass 500. Then there is a dense layer, then a batch norm leaky ReLU, then I'm going to reshape. All this kind of things is going to make sense. Okay, so don't really focus much on this. This is just for me as a guide to build a whole model. Okay, so that I don't need to look into paper again and again. I've just taken a summary over here. So for that, I'll just create a function called as um, create generator model or build generator model, whatever you like to call it. Okay, it's completely your call. Whatever you like, you can call it. I don't really need to pass any inputs. You can give, like, input dimensions if you want, if you're going to change it. But in my case, I'm just going to keep it as 500. And like, this kind of project is not going to focus more on documenting the code and making it very efficient. Even though it's going to be still efficient, but I'll show you techniques through which you can do this kind of projects in a great way in one of our upcoming module, where we're going to use the same data set, but yeah, you're going to see the difference between this and that. Only few kind of lines of code will be different, but that will be more efficient, where we'll be having multiple functions, unlike what we're going to have over here. You're going to realize it very soon. So I'm going to build a generator model with the help of tf.keras.sequential. So with the help of sequential API from Keras, I can build my model where I can keep on adding the layers in a sequence. How exactly? Let me show that. So model.add, I'm going to first of all have an input layer, and I'm going to get this layer from the layers that I've already imported previously. If you guys remember, I done the import of tensorflow.keras.layers, right? So that's what I'm referring to. So yeah, this is the layers input, and if I press Shift Tab, I need to give shape as equal to 500. That's it. After this, what do I need to do? I need to connect this with a hidden neuron, I mean a hidden layer, with the help of this dense layer. So model dot add layers dot dense. And then the shape that I'm going to pass over here would be 4 cross 4 cross 1024. And in all of the layers, as mentioned in the paper, we are going to turn off the bias. We are not going to use bias. By default, bias is going to be used as true in TensorFlow layers. So if I just press Shift Tab, you can see that there is an input called as use bias that is set to true. I'm just going to set it to false. And now what is the reason I have specifically chosen this many neurons for my hidden layer? My first layer is going to be input layer with the 500 random values. Then a second layer is a hidden layer called as dense layer in Keras with this many neurons. Why specifically this? Well, you're going to understand it in a while. Okay, so we are done with the dense layer. Then we are having model dot add layers dot batch normalization, where it's going to normalize this inputs with respect to batch axis. And then I'm going to add layers dot leaky ReLU. And by default, whatever is the negative slope, that's what we're going to use 0.3 and not going to change anything over there. So this is one of the activation function that we have. Just like ReLU. In ReLU, what happens? If we pass any negative values, it's going to convert to 0. If I pass any kind of positive values, let's say 2, it's going to keep it as 2 only. If I pass an 8, it's going to keep 8. But if I keep negative 4 as an input of leaky ReLU, it's going to convert it to of normal ReLU, it's going to convert it to 0. If I talk about leaky ReLU, the positive values have no difference as compared to normal ReLU. If I give 2, it's going to be giving me 2. If I give input of 3, it's going to give me the output of 3. But for the negative values, now my values are not equal to 0 every time. I'm giving some kind of a slope over there of 0.3 so that I keep on getting some negative values over there as an output instead of just getting 0. And trust me, whenever you're using GAN, using leaky ReLU is the better option as compared to ReLU. You can go ahead and check it by yourself only by converting this to ReLU. But now we are done with this block of code. Now I need to reshape the image to 4 cross 4 cross 1024. So I'm going to have model dot add layers dot reshape, and then I'm going to pass a tuple of 4 cross 4 cross 1024. And again, there is a reason behind why I am doing this. I'll return this as a model just to check if it's working fine or not. I'll copy this. I'll say that I want to create my dummy model with the help of build generator model, and I'm going to check the summary of it. Okay, I'm having some kind of error. Let's try to figure it out. Cannot convert 500 to a shape. Let's see what's the problem that we are facing over here. We are having the first input layer of shape 500. Okay, I guess I need to have this as a tuple. Only then it's going to work. And now if I try this, yes, it's working fine. So initially, if you just multiply all these values, it's going to have 16384 neurons, 16,384. So from first 500 neurons in the input layer, you're connecting them with 16,384 layers. Then what do you do next? You add a batch normalization layer and a leaky ReLU, and then now reshape it into a 3 dimension that is 4 cross 4 cross 1024. If you want to give a batch size, you can give it, or else you can keep it as none by default. There is no problem. So now from this 4 cross 4 cross 1024, I want to get the shape of 128 cross 128 cross 1. Okay, 128 by 128 by 1. That's what I want. Because yeah, that's the shape of the outputs that my generator should be producing. So how can I do this? I can do this by stacking blocks of count 2D transpose on top of each other. But according to the paper, we are also going to use batch norm and leaky ReLU. For each con2D transpose, I'm going to use a 5 cross 5 size filter. You can obviously change this, but according to the paper, that's what we are having. keep bias as false. Going to start with 1024 filters and end up with 32 in the last one, and have a stack of 5. Why a stack of 5? You are going to understand because of the shape that we want to have. So for this, I'll have my first up sampling block using con 2D transpose. So model.add layers.con 2D transpose. What do I give as an inputs? I need to give filters, then kernel size. So the first filters I'll be using from 1024, I need to change to 512. After this, I need to give the size of the filter, which is 5 cross 5. Then I also need to provide padding is equal to same, because convolution is going to decrease the size if I don't use padding is equal to same. And after this, I need to use bias is equal to false. And then strides is equal to 1 cross 1. What is the reason 1 cross 1? Because yet I don't want to increase directly from 4 cross 4 to 8 cross 8. If I want to do the doubling part, I need to use strided convolutions of 2 cross 2 directly. So that's basically like, the part that has been explained over here. That for the first layer, okay, we are going to use a normal stride convolution that is 1 cross 1. For everything else, we are going to use strided convolution to double the size when we use strides of 2 cross 2. Okay, but for the first one, I'm going to use it as 1 cross 1, again as mentioned in the paper. Then model.add, I'm just going to copy paste this layers and have it over here. So that's my first block ready. Like this, I need to have another 4 blocks. But before that, let me just run this and see if it's working fine. So this was the reshape layer. After that, I decreased the number of channels by keeping the same shape. And yeah, everything is fine. Now let me have one more stack where I'm going to just copy all of this and paste it and say that this is my second upsampling block, where now the size of the filters, or I should say the total number of filters, will be the half of the previous one, which is 256. And I'll double the strides to double the size of the image. Run this and check the summary. So as expected, now it's from 4 cross 4 to 8 cross 8 with 256 channels. Now just like this, I'm going to copy it for 3 more times. And just change this to third upsampling block. I need to decrease this to 128. Strides will be to everywhere. This will be now 64. This is my fourth, and this is my fifth. This will be half of that 32. Now let's try to check the outputs. So over here you can see that from 4 cross 4, 8 cross 8, 16 cross 16, 32 cross 32, 64 by 64 is what we have reached. Now comes one final layer of con2D transpose that's mentioned over here, with only one filter and activation as 10H. What is the reason behind that? Because I want to produce the outputs in between -1 to 1. And currently, if you see, there are 32 channels. I just want one channel. So for that, I'll need to have only one filter. So I'll have final layer as model.add layers.con2D transpose. One, I'll still use 5 cross 5, padding as same, use bias is equal to false, and strides of, because I still want to upsample, I'll use strided convolutions, and I'm ready to run my final summary. So as you can see that we are finally having 128 by 128 by 1 as the output. If I want to make it more efficient, I could have just created a function for these blocks where I could have simply omitted to use this kind of copy pasting. That's a better way of coding. But all this kind of a better things, efficient way of coding and also getting the outputs from the training, I'll show you in one of our upcoming modules. So no need to worry about it. This is just to help you get started by building your first generator model with the help of con 2D transpose layers. Okay. And yeah, this is the kind of model that we have built. Currently, it's having 25 million trainable parameters. And according to the extra parameters that we have from the batch optimization layers, we are having total of 34,752 of them, which is not going to be trained. It's just the scaling and all that kind of factors, which does not affect the training. And yeah, that's about basically, sorry, the what do you call this, the model parameters that I used to talk about is not about the scaling because that's what is going to be trained, but this is about the mean and the standard deviation, which are the part of non-trainable, but you can skip that part. Okay, no need to worry about it. So that's our generator model that we have finally built the way we wanted it to be. And yes, I'm not really focusing on getting the best model. That's something that I'll allow you to go ahead and do that changes. For now, this is the model that I'm happy with. Now what I'm going to do is I'm going to go ahead and create my discriminator model in step 4. Discriminator model. And to know about this, stay tuned. I'll see you in the next video. Now, before we go ahead and talk about the discriminator model, I actually had to also show you how the generated outputs are going to look like. So what have I done? Let me just go ahead and comment these codes. So build the final generator. Above one was the dummy one. Create noise for input, where we know that the noise must have 500 values per single image. From here, I'm going to convert it to 128 by 128 by 1. Generate fake image of shape 128 by 128 by 1. And I'm calling this generator and passing the input as the noise and keeping training is equal to false because I'm trying to not train my model. I'm trying to use it as inference over here to get the outputs and generated image. The output that we got over here, I'm passing it in the imshow command of matplotlib.pyplot. This is for the batch. This is for the rows, columns, and the channels. So I want to use the first image of the batch. I'm giving the color map as gray, and if I run this code cell, you can see that all of these values are random. What does this random.normal actually do? If I show you over here, if I press comma, it takes random values from the normal distribution whose mean is 0 and standard deviation is 1, which is basically your standard normal distribution if you're aware about it. And I'm not using any kind of seed value, so I keep on getting random values over here, so that if I again rerun it, it's going to be some different noise and you can see the output. It's completely random because we haven't yet trained our generator. The moment our generators are going to be trained, it's going to take this kind of appearance like what you see over here, 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 and here, right? So let's go ahead and now build our discriminator. I hope that the idea of how to get outputs from the generator is now clear to you. For the discriminator model, we know that it's a binary classifier where the outputs is going to be if this is a real image or the fake image, right? So the final output is going to have only one neuron. Either it's real or it's fake. But now to prepare a binary classifier, I'll need to have stack of convolution layers, leaky ReLU activation, and dropout for 5 times, where I'm going to use strided convolutions. Again, the filter size over here will be 5 cross 5, and the total number of filters are going to be from 32 to 512 in this 5 blocks. Again, this is from the paper, and I'm directly having the summary over here. And some of the things I might have altered over here, but yeah, you're going to see it in a while. So I'm going to create my build discriminator model. Again, I'm going to build my model with the help of tf.keras.sequential. I'm using my sequential API to stack my layers in sequence with the model.add layers.con to d. I'm going to use 32 filters, 5 cross 5 filter size. This time I can use bias, so no problem over there. I forgot to give input layers dot input where shape will be 128 by 128 by 1, right? Even the real image or the fake image by the generator both have 128 by 128 by 1. So that's the input. This is the con 2D. I'm going to keep padding is equal to same, or else I'll be reducing the image size. And now let me return the model and create dummy model again for the discriminator part, and dummy model.summary, just to keep on checking that we are getting outputs the way we want. Well, I also forget to mention the strides of 2 to decrease the image size by half. Typically, in the image classification models, you must have seen the stack of con 2D and the max pooling 2D. But that's not what we are using in the GAN. According to the paper, they have researched about it and said that using a strided convolution was giving better outputs as compared to the max pooling 2D. So I'm going to use strides of 2 cross 2. And now the image should be 64 by 64 by 32. So yeah, that's correct. I'm going to have a leaky ReLU again with respect to the paper. And then dropout is optional. If you want to add, you can add it. Okay, I'll just create lines in between. Layers dot drop out. I'm going to drop 30% of the values from the leaky ReLU layer. So randomly, 30% of the values are going to go to 0. Now this is for the regularization purposes. Okay. Randomly for every epoch, randomly every time it will be some different values. It's going to take it and convert it to 0 for the regularization purposes. And again, this is optional if you want to add it. So I'm having a con2D leaky ReLU and the dropout. And I'm going to have it for 5 times. One time is already done. So 4 more times. 1, 2, 3, 4. And from 32, it's going to go to 64, 128, 500 and 256, and 512. And finally, I'm going to flatten the layers dot flatten and add my output layer with the help of dense. Just keep in mind what have we done so far. We have added convolution to the block 5 times with different filter sizes with strided convolution, leaky ReLU, and dropout. Then we used flatten and finally the dense layer. I can surely go ahead and use my activation as sigmoid. Oh, sorry. Over here, to be honest, I'll show you how I'm exactly going to do while actually building the model. At that time, I guess I'll be using it in the optimizer part or during the compilation part. Okay, I guess you will be seeing the reason behind, like, why am I not adding sigmoid over here? But if you want, you can have activation is equal to sigmoid. because we are using binary classification task. Let me just add it over here. There are multiple ways through which you can have the effect of sigmoid even later on or over here. It's completely up to you. Note that the task of the discriminator is to give you the output in between 0 to 1, and therefore sigmoid is what I'm going to use over here. I'm going to run this code cell, and so you can see that that's how it's going to work. And finally, 1. You can also have fully connected layers over here if you want, if you don't directly want to go to 1. Again, it's your choice. Okay, this is just a kind of a model that I'm making over here to make things work. You can surely go ahead and make this model even better, right? So yeah, this is the discriminator model that we have built for our GAN model. Now I'll just make sure to get the outputs from the discriminator, because we are already having the fake image that we have got from the generator. Let me pass this generated image into the discriminator and check what kind of decision it's going to make. Okay. So for that, first of all, I need to have my discriminator model, pass the generated image, and then print the decision. So discriminator is equal to build discriminator model, decision is equal to discriminator generated image, and then print decision. So it's 0 0.5. It's neither closer to 0 or closer to 1. It's approximately 0 0.5, because currently it is not able to have any kind of decisions, right? So yes, this is what we have done over here by creating our discriminator model. Now in the next video, what we are going to do is we are going to come up with the laws and the optimizers for our GAN model. And then later on, we'll talk about how we are going to create the training for this GAN model. Because just think about it. We are having two different models that are going to train simultaneously. So how is it going to work? Are you just going to use model.fit or something else? Stay tuned about understanding how all of this is going to work. However, for the next video, I'm going to talk about the loss and the optimizers. So now to define our losses and optimizers, let's first talk about losses. And for that, there is actually one thing that I'm going to implement, because I'll be using binary cross entropy for both of these things, okay, for my generator as well as my discriminator. And the way that I'm going to do this is by creating a helper function that is called as cross entropy. And this is one thing I'll be using every time. And how am I going to have my binary cross entropy? With the help of tf.keras dot binary, oh wait, it's losses dot binary cross entropy. Okay. Now inside this, if I give from logits is equal to true, it's going to do the calculations of sigmoid. Okay. So that's why you can avoid writing it over here, or else if you're writing activation sigmoid over here, in that case, what you can do is you can avoid writing from logits is equal to true in this case. Okay, so either of it is going to work, whatever suits you the best. So I have created the helper function named as cross entropy that will be used to define losses for generator and discriminator models. How exactly? Let's talk about discriminator loss. So remember, for the discriminator, I am going to give two different inputs: a sample of a real image and the output that is generated by the generator. So I'm giving two different inputs, and therefore I'll be having two different losses that I need to calculate. And for that, I'll just define this as, let's say, discriminator loss, okay? And then give the real output and fake output as an input to this losses. So real output and the fake output, okay? This is the sample from the data set. This is the output from the generator. And then what am I going to do? I'm going to calculate my discriminator loss because of the real output and the fake output. So you can call it as a D real, D fake, or whatever you would like to call it, doesn't really matter. Okay, so I'll just call it as D real in order to calculate my discriminator loss because of the real set of image. How will I do it? I'll call cross entropy function, okay, and then while calculating the binary cross entropy, what do we need to give as an input? If you remember, the formula is going to be something like this. Okay, minus of y into log of probability of that y minus 1 minus y into log of probability of 0, which is 1 minus p. So this y are your true values that will be either zeros or ones, right? So in this case, I need to go ahead and say that if I'm calculating my loss for the real images, I need to pass ones because ones will be true, zero will be false. So how can I get this ones, right? I can get this with the help of tf dot ones like, tf dot ones like. So for the cross entropy, the first thing would be the true values and then the predicted values. So the predicted values are nothing but the real values in this case. So that's how we have defined our discriminator loss for real set. Now I'm going to do it for the fake one. That will be exactly in the same way. The only difference over here that this is zeros likes. Zeros like. Why? Because it's a fake and I'm going to have zeros for it. And over here it's going to be fake output. Right? So that's what I'm having to have my fake loss for the discriminator. Now, what is the final loss of the discriminator? It's basically the summation of both of this, right? So I'm going to return d real plus d fake as the final loss, or else I can also do like d loss is equal to this. Whatever suits you guys, okay, you can go ahead with that. And the reason it got pasted over here is because by default, like I pressed Alter and tabbed somewhere else, so it produces multiple cursors. But anyways, I'll just solve it like this. So that's my discriminator loss. What have I done? I've passed the real output from the data set. I've passed the image from the generator, then created the cross entropy. For the real, I passed ones like as the true output and real output for the the predictions that we are passing to that cross entropy model, and the fake output for the fake loss basically, and then combine both of them to get the final discriminator loss. Now it's time to create generator loss. Remember, the job of the generator is to fool the discriminator. So the output of the generators, even though are fake, I need to tell my model that what, this is what you need to produce. So I'll give it as one. You will understand it once I write it. Generator loss. I'm going to give fake output as an input to the generator loss. And I'm going to have my G loss is equal to, I'll copy this and paste it. But instead of zeros like, I'm having ones like, because that's where my generator is going to understand that I need to produce outputs like this closer to one from the current outputs that is able to produce. And that's how my discriminator is going to be fooled. So yes, that's how I'm having my generator loss, which I'm going to return as an output of this function. And I'm going to run that code. So I am ready with my generator loss as well. Just make sure that the discriminator and the generator optimizers are different, since we are going to train two networks separately. So now for the optimizer part, just like what we did for the losses part, I'm going to have two different optimizers. For now, I'm going to have both of them having the same learning rate, that is 10 to the power of -4. So let's see how we can go ahead and edit. So I can call it as generator optimizer, or else I can just call it as G optimizer is equal to tf dot keras dot optimizers dot adam. Adam is what has been used, and I'm going to pass the learning rate of see over here the beta 1 and beta 2 values are going to be exactly the same, so I'm not going to change it. I'm just going to change the learning rate to 10 to the power of -4. And exactly the same thing, no difference for the D optimizer, right? And yeah, that's it. This is exactly what I wanted, and I need to run this code cell now, right? So we have successfully defined our losses and optimizers. Now, in the next video, I'm going to show you how we can save this kind of optimizers, the state of discriminator and generator after every certain epochs. We can do it with the help of checkpoints. Okay, and that's exactly what I'm going to teach you in the next video. So yes, stay tuned for this, guys. And remember, in the upcoming projects, because we are dealing with GANs, more or less the codes are going to be very similar. So it's really important that you're understanding everything in this module, because later on, because I've already explained all these kind of things over here, I won't be going into great detail by writing everything. I'll show you the code. However, still I go with the step-by-step explanation, but not with the great detailings that I'm doing right now. So yes, make sure you are having proper attention, and I'll see you in the next video where I'll talk about checkpoints. Now, it's really important that you think about this point, that during deep learning tasks, it's going to be very time consuming depending on how many epochs you're going to train your model for. So always remember, whenever you're having long running tasks during training, the chances of getting interrupted will be pretty much high because of some or the other reasons. And checkpoints is a way through which you can solve this problem. That is, you can save your checkpoints at certain intervals, or maybe after every epoch, it's your particular wish, and then restore the model to use that specific checkpoint that you want to use. Use the latest one basically. Now you can deal it with this in a lot of different ways. I'll be showing you one way in this notebook, another way in some upcoming notebook, in some second or the third module. All right, so yeah, let's go ahead and check about how we can set up our checkpoints in order to save and restore the models. So the first thing I'll be doing over here is to set up my checkpoint directory. So I'll just create a path called as training checkpoints in my current working folder, and see how is it going to work. Checkpoint path. Okay, so checkpoint path or checkpoint directory. So in the current location, I'm going to have training checkpoints. Now I'm going to create a path. Okay, you can call it as checkpoint prefix, where I'm going to use os.path.join, where I'm going to pass my checkpoint directory, and then create one more folder inside this called as checkpoint ckpt. And that's the setup. Now create the object for the checkpoint. That's not where you actually saving it or restoring it. This is just to initialize your checkpoint, just like what we did for the loss part over here, right? Then later on we'll be using it during the training process. Okay. So as I mentioned, there are multiple ways through which you can manage your checkpoint. I'm just going to show you one of them right now. So this checkpoint is equal to tf.train.checkpoint. Okay, that's what we are going to use. Now, as an input, I'm going to pass my discriminator model, generator model, and also the informations about the optimizer, because the weights and the biases, basically the trainable variables from the generator and discriminator, will be saved along with the state of the optimizer. So I can go ahead and say that shift tab, and if I can show it to you over here, there is some example. Or else I can just go ahead and do it for you. So generator is equal to generator, then discriminator is equal to discriminator, then generator optimizer will be equal to G optimizer in our case, and discriminator optimizer, it's equal to D optimizer. So for this checkpoint, I have asked it to save my generator model, which I have defined as generator somewhere. And for the discriminator, it's going to be discriminator. So yeah, that's what I'm having over here, generator and the discriminator. And then uh, G optimizer and the D optimizer for the optimizer parts. Just copy this, optimizer, and I'll run this code cell. So now what's going to happen over here is, if I show you, in this working directory, the outputs basically from the Kaggle, whenever you're going to save the checkpoints, it's going to use this root directory for the checkpoints, inside which you're going to have another folder called checkpoints. Right? Inside this, there will be one folder called training checkpoints, inside which there will be one another folder called as checkpoint, inside which you will be saving different checkpoints. And the latest one, you can use it to do your inference later on, or maybe not just inference, but resume the training actually. You can do both of them, there is no problem, right? So yes, with the checkpoint manager, I'll show it to you probably in one of the upcoming videos. For now, let me just show it to you that how we can do it with the normal save and the restore options, okay, without the checkpoint manager. But for that, I'll need to set up the whole training loop, the custom training loop for the GAN, but yet we are not there. Okay, I'm going to go ahead and set up some of the uh, things before that, that is going to be useful for the training, and then build that training step. Okay, so yes, I'll see you in the next video, where I'm going to create a function that's going to help me generate and save images after every epoch. Okay, and so yeah, I'll see you in the next video. So in order to create our generate and save images function, I'm going to need three different inputs. The model that's going to help us understand that yes, I'm going to pass a generator model on which I'm going to have a prediction to get the outputs from the generator. And the inputs it's going to receive is again going to be passed from this same function. And for which epoch I want to get this output, even that information is being passed inside this function. So what will be the first step over here? The first step is to generate the predictions. So let's try to do that. So for that, what will I need to do? I'll need to pass my test inputs inside the model, and then keep my training is equal to false, because I'll be running this in the inference mode. Just remember that we are also having batch normalization layers. So yes, I'll be using in the inference mode. So I'll have predictions is equal to the model in which I'll be giving test input, And that's what is going to give me the outputs, the generated outputs, the whole 128 by 128 by 1. But I'll run it in the inference mode by keeping the training is equal to false. So once I got the predictions, according to the total batch size that I'm having per batch, I can now display the outputs as a subplot. I'll be choosing right now 9 by 9. That's my number that I'm having over here. Later on, I'll also show you 36 total images, 6 by 6 outputs as well. But right now, I'm going to have my for I in range of what? The batch size. How do you get the batch size? The first axis in the predictions, you are having that batch size, right? If you remember the shape of these predictions, it's going to be batch size, comma, rows, columns, and channels. So I'm going to have from predictions dot shape of 0, I'm going to get multiple I values, and then plt dot subplot of 3 cross 3 cross I plus 1, and then have plt dot im show of the predictions of that I. But this with all rows, all columns, and all channels as well. All right, that's how the prediction is going to work. And because it's also a single channel outputs, I'll also give color map as gray. Then I can turn off the axis, right? And I can also give some kind of figure size for us with the help of plt dot figure. I'll keep it as 10 cross 10 for now. Now after that, I'm also going to save this figure with the help of plt dot save fig command. Okay, so plt dot save fig, but along with it I'll also give one more, that is plt dot tight layout, just in case if I want to adjust some kind of spacing between the subplots, I can do it. Then save fig. What do I need to give over here? I just need to give the name of the figure that I want to save. So it's image at epoch, right? Image at epoch, and then correct to 4 decimal places. Whatever you would like to write, you can just go ahead and write it. And the way that I write it is as image at epoch, and then I'll have my curly brackets, and with this I'll have for d dot format, and also dot png. I can't forget that, right? Because the you can also save it as JPEG, right? I'm just using PNG, and then the name of the epoch, the current epoch, basically, right? That's what we are going to have. And once this is done, I can just show the outputs if I want, right? And I'm done. I'm going to run this code cell. There are 2 commas that I've given, no problem. I'll sort it out. So the function to generate and save images after every epoch is going to be running like a charm. So for every epoch, I'm going to give this value that will be saved over here. So after that epoch, I'm going to save the figures. That's great. So yes, guys, that's how we have created our function to generate and save the images after every epoch. Now it's time to go ahead and build our one single train step. Okay. And then later on, we are going to use that one single train step to generate the whole training. So let's see how exactly we can build this up. So in the next video, I'm going to show you how to build up one training step where you can train your generator as well as the discriminator simultaneously. We are going to do it with something called as gradient tape that we are having in the TensorFlow to calculate the gradients and also update our trainable variables. So yes, stay tuned for that. I'll see you in the next video, guys. So now in order to create one training step, what have I done? I have defined a function called as training underscore step. But now there is something on top of that that is called as at the rate tf dot function. So what is this? Well, this is the decorator in TensorFlow, which is used to convert a Python function below it into a TensorFlow graph or a TensorFlow graph function, where the whole idea is to improve the performance by optimizing the internal computation. And basically, we are having two major benefits over here. First of all, we are having this kind of graph conversion from the normal Python functions that's going to be more efficient representation for TensorFlow operations altogether as compared to the default Agar execution, which overall impacts the performance. So by compiling the function into the graph, the TensorFlow can basically optimize the computation and execution, which altogether will improve the performance. And we use it especially in the scenarios where whenever we are involving, let's say, large models or the data sets. And one important thing that we are going to use it over here is for auto differentiation. TensorFlow can perform automatic differentiation in a much more efficient way on graph functions, which will be beneficial for our training GAN model. Because as I told you, we cannot directly use model.fit. So this is the alternate way of training the model. So yes, it's going to make sense once I'm going to write the code and help you understand it even better. So yeah, let's get started by understanding the first line of code that I'm going to write for this function. So I'm going to pass the batch of real images. So I'll also need to generate a data for noise, which will be used to generate some kind of output from it, which will then be compared with this real batch. So for that, what will I do? I'll generate random noise, just like how I explained to you in the previous I should say in the previous videos. That's going to be define noise. So noise will be equal to tf dot random dot normal. Okay. And now I need to pass the shape. What is the batch size, right? I need to pass the batch size. If I remember it correctly, I had defined batch size somewhere. I hope I had defined this earlier. Let me check. Um, Batch size is equal to 64 is some I guess 64 is what we had defined. Okay, never mind. We'll just define it later on if we haven't defined it. If I'm able to remember it correctly, I had defined it somewhere where I asked you to change it later on. But yeah, let me just cross check it. Yeah, 64. So by default, I have used 64 over here, but I can define this as batch size, which maybe I can write it separately about what is the batch size that I want to use. So yeah, let's do one thing before we actually define one training step. I'll I'll also add one extra code cell where I'm writing my batch size. Okay. So my shape will be equal to the batch size. So that many images I want to generate of the dimensions 500. Okay, I can also define my input dimensions as 500 if I want. Okay, and even for the generator part, I can make it in a better way by calling this as input dims. Alright, where batch size for now, I'll keep it to 64 or maybe 32, whatever it is, I'll keep it 64. The dimensions are 500, right? So this is the total noise per batch, and it's going to be taken again from the normal distribution with mean 0, standard deviation is 1. So yes, we have defined noise as the first step for our generator. Now we are going to use something really interesting. We're going to have gradient tape from TensorFlow, one to update generator optimizer and one to update the discriminator optimizer, basically by updating its model parameters. So how can we do this? We can use with tf dot gradient tape as generator tape, comma tf dot gradient tape as discriminator tape. I can just call it as discriminate tape. What is the first thing I need to do? Once I'm having the noise, what will be the first step I'll be doing? I want to train my generator by showing the noise, and then at the same time also want to get the output for the same. So I'll have generator is equal to generator input will be the noise, and training will be kept to true. Training will be kept to true. So what is this actually? This is the generated images per batch, right? Fake batch is what you can name them. Now, after this fake batch, what's going to happen? I'm going to create outputs for my discriminator for the real images as well as the fake images. And in both the cases, I'll keep the discriminator training status to be true because I also want to train my discriminator. Right? Once my generator is trained, I also want to train my discriminator. So I'll have real output is equal to discriminator, where I'll be passing the real image batch and training will be equal to true. Similarly, fake outputs is what I can use. So discriminator, this time I'm going to give fake batch. I can call it as fake image batch, fake image batch, and keep its training to be true as well. Great. So now I'm having generated images from the generator and two different outputs from the discriminator. Now I'm going to calculate my generator loss and the discriminator loss. So if you remember from the step over here, discriminator loss will have two things, real output and the fake output, right? And we are having the real outputs and the fake outputs that we are going to use for the discriminator loss. And for the generator loss, we are just going to have fake outputs, right? So given this, let's go ahead and create the losses for the generator and the discriminator. I'll just check it for once. The first is real, the second one is fake. Okay. So I'll also have a comment. By the way, because of the gradient tape, you are going to update, first of all, calculate the gradients and then apply those gradients to update the trainable variables that are the model parameters, weights, and the biases. So yeah, that's what I'm doing over here. The first thing is to generate the fake images from generator, then get real and fake outputs from discriminator, get the losses for GAN and disk models. So let's say I want to have my generator loss. I'll just call it as GAN loss. And how will I have it? I have defined the name of the function as generator loss. Okay. Where the inputs are going to be fake outputs. Then disk loss will be equal to discriminator loss, real outputs and fake outputs. Right? So that's what we were having over here. Real output and the fake is what we had to give, and everything looks good. So this is to calculate the loss. Okay, this was to calculate the loss. Now, how do you define the gradient, or how do you find the gradient? I told you, right? Whenever you use at the rate tf dot function, the auto differentiation is going to work like a charm. And that's what I'm going to do by using dot gradient on this generator and the discriminator tape to get my outputs of the partial derivatives of the loss with respect to the trainable variables. So how can I get it? So gradients for generator will be equal to, with the help of GAN tape, I can calculate gradients. Okay. Now the inputs are target, comma, sources, which basically means the loss with respect to the trainable variables, right? That's how I can get my gradient. So generator loss, comma. Now from the generator model, I want trainable variables. That's how I'm going to compute my gradients for generator. Now I'll just copy this, paste it for my discriminator. And I'll be using my disk tape to calculate the gradients for disk loss and for discriminator trainable variables. It's not non-trainable, it's actually the trainable variables, right? So that's what we have defined, where we have to calculate the gradients using the respective gradient tapes. Now, once we are having the gradients, what's the next step? That is to update the model parameters by applying the gradients onto the optimizers. So we'll have our generator optimizer and the discriminator optimizer. I'm going to zip all the gradients and the discriminator values. Sorry, I'm going to zip the gradients from the generator and the discriminator with respect to the trainable variables of the generator and the discriminator. And that's how the model is going to train for one single step for both generator as well as discriminator simultaneously. So now it's time to update the model parameters. So generator optimizer dot apply gradients, where I need to zip. What do I need to zip? What are the gradients? So that's gradients for generator. And on what do I need to apply this? I want to apply this to the trainable variables of the generator. So copy this, paste this. Similarly, doptimizer dot apply gradients, I'll have exactly the same thing, but for discriminator. Copy, paste, copy the discriminator and replace it with generator over here. Simple as that. So that's exactly where we are going to update the trainable variables or the model parameters. And that's how I'm going to complete my one single training step. And how have I achieved this? I have achieved this with the help of the TensorFlow decorator called as tf.function, where again, just to revise, we are able to get this kind of auto differentiation ability, which is going to happen much smoother with the help of TensorFlow graph functions than the normal function. And to get that done, we are using this decorator. Okay, so I'm going to run this code cell. Hopefully, there are no errors. And yes, there are no errors. Okay, and I'm also going to run this code cell. And to be honest, I'll just cut this code and have my setup ready on the top over here. Okay, the batch size and the input dimensions are what I'm going to define over here. Great. So during the whole epoch, in one single step, this is what is going to happen. I'm going to pass a real image batch that I'm going to fetch from the dataset that I've created over here. If you can remember. So yeah, from this dataset, I'm going to take one batch for one single step. I'm going to have one batch. So for one batch, I'm going to pass this real images, and the fake batch is automatically going to be created because of the noise that we are creating inside of the training step. So we don't have to define it externally. Internally, it's going to produce different random noises taken from the normal distribution of each the same batch size as our real image batch. And then the same process of the generator, the discriminator is going to be done. From that forward propagation, we get our loss values, and from that, the back propagation happens where we're having the gradients, and then we apply the gradients to the respective optimizers, right? So, marking this the end of the video over here, we have understood about how to define one training step for the complete training. Now in the next video, I'm going to go ahead and create a function that's going to help me train my whole model, where internally it's going to call multiple training steps. How many training steps? It will be equal to the the value of batch size, sorry, the total examples divided by batch size. That would be the value that we'll be having as one single step used, sorry, as one epoch. Okay, so inside one epoch, those many steps will be there, total images divided by the batch size. So yeah, I'll talk more about it in the next video, so stay tuned for that, guys. So inside this function, we are going to pass the data set that we have already built, and from which epochs do we have to continue the training process. So I'll remove this pass, and let's get started by understanding what all kind of things I'm going to pass over here as an input for training my whole model, right? So inside this function, I'm going to train per epoch, and per epoch, I'm going to have multiple steps. Okay. So what am I going to generate first of all? I'm going to generate for epoch in range of total epochs. So for epoch in range of this epochs, what to do next? I am going to start the timer, because if you remember, we had downloaded, or I should say we have imported the time module to time our epochs. So the start time will be equal to time dot time. That's how the timer is going to start. Now inside this epoch there are multiple steps that's going to go ahead. Now how to show the progress of training per epoch? There are multiple ways. Okay, I'm going to show you with the help of TQDM. Well, TQDM, I guess, is one of the word that we use in Japanese or Chinese. I'm not sure actually, but either of it, we use it to show the progress. Okay. So from TQDM, I'm also going to import TQDM to show the progress, or else you can simply print dot after every step is completed. Okay. Either of the thing you can do. For this project, let's say I'm showing you TQDM. Later on, I'll also be using the dot method as well. Okay. So inside this epoch, and now what I'm going to do is I'm going to get image batch from the data set. So from image batch in TQDM data set, this TQDM I have to import it because I remember I haven't yet imported it. I'll remove this because I have not used it anywhere, and I'll say that from TQDM import TQDM. What's going to happen? It's going to show me progress per step from 0% to 100%, so that I'm not bored. I'm able to see that, okay, how much time is taking per step, and then finally how much time per epoch. So if I scroll down, so inside this image batch, what do I need to have? My training step, where I'm going to pass my image batch, which is real, because this is the real data set from which I'm getting the image batch. That's your real image batch. So the training step is going to happen for all the batches that is present in the data set. After this is done, what's next? I want to display the outputs that I've been generating with the help of generator. So let's say if there are any kind of existing outputs, I first need to clear the outputs, right? So I can do this with the help of, I guess, I had imported IPython displays somewhere. Yeah, IPython and displays there. So display dot clear output, and then wait over here is to clear the output until the new output is available. So yes, I'll be using my wait is equal to true. And I'll also document this code a bit. Train one epoch. Train steps per epoch. Clear the output screen before displaying generated data. Okay, so yeah, that's what I'm going to do. First of all, I'm going to clear the output. After that, if you remember the function that we had created, generate and save, that's what I'm going to pass as an input to get that output. Display the images, right? Which model am I going to use? I'm going to use generator. And inside this, if you look at the epoch, my epoch is going to start from 0. So I need to have just +1 to make sure the value of the epoch is not starting from 0. If I show you the function, this epoch is used to mention image at epoch. So I don't want to write image at epoch 0. I want to start it from image at epoch 1. So that's why I'm having that plus extra 1. Now, what is the test input? Well, I'll be creating a separate test input which is going to be used inside this loop, and the same image or the same set of images will be used to display the output. So what's going to happen? We got one batch from the real data set. Inside the training step, we are generating like different random batches. But then what is this test input? This is to generate and save the images. So the same type of images will be kept on generating. So I need to define this test input somewhere. I'll call it as SID test for or I'll just call it as SID data. Okay, and maybe I'll define it somewhere here, or maybe I'll just define it somewhere later on only. But yeah, that's what I want to define. Okay, SID data, SID data, which is going to be tf dot random dot normal, and yeah, I'll fill the details later on. So inside of the training steps are completed, the outputs are wiped, and then I'm having generate and save images function which is called. After this, it's time to save the model after every n epochs. Now that n epochs is your choice. I'm going to have after every 15 epochs. So if you remember the checkpoint that we have created, I'm going to use this checkpoint to save the status of the model and the optimizer after every 15 epochs. Save the checkpoint after every 15 epochs. And to be honest, the randomly that I'm having my data spread here and there. That's how you actually go about it. And then later on, you document it by keeping all the things that you required in the project notebook all together somewhere like this. And in the next project, we are going to start by defining all the things that we'll be requiring, and then build on different kind of functions and finally get the training done. But for now, that's how we are going to go with. If epoch plus one is a multiple of 15 or divisible by 15, then I'm going to use my checkpoint to save the status of my models and the optimizers. And the file prefix that I'm going to use this checkpoint will be the prefix that I've defined earlier. Okay, so file prefix, and that is something that I have defined over here and paste. Great. So after every 15 epochs, my checkpoints are going to be saved. And I also want to display the time it took per epoch in seconds. So how can I do it? I'm going to have a print statement. I'm going to have a f string, or I can use formatting of the strings in the way I want. Uh, let's say time for uh, epoch is my current time minus start time, seconds. So that's how I'm documenting per epoch how much time it took to train it. Now let's say once whole of the training is completed, okay, once my display will be clear, sorry, after all the training will be completed, there will be the final epochs output that will be left. So what I'll do instead is I'll generate one final result after the final epoch is completed. So for that, what will I need to do? I'll need to first clear the screen, right? So I need to come out of the loop. Okay, till now what we have been doing was inside of this loop, which does not make sense because this is one epoch which will be done, and this is not what I want to have. Uh, so this was for the, what do you call it? This was for the steps, right? And here is the epoch. So for the epoch, I require it, and all of this is outside of the code. So I'm good. Yes, I'm good to go. I'm going to come out of the epoch because after every epoch, I don't want to do it. I want to do it for the final epoch. After the final epoch, display the outputs. So for that, again, you need to first clear the outputs and then pass this generator model and the total epochs that we had passed as an input and the seed data. That's how we are going to generate our final outputs. Now, let me also prepare some extra things that we might need. The only thing that we need is the seed data. So over here, what will be the shape that I want to produce? I want to have 9 outputs to be produced, and the dimensions are going to be same as input dimensions, the 500. So I'll just take this up only. I'll define it on the top. Images, number images for output display. That will be 9, And this is my seed data tf dot random dot normal, which shape is equal to, I will be having 9 images to display, each having input dimensions. And I'm going to run this code, sir. And I'm done. So our training function is ready. I'll run this code cell. Hopefully no errors over here as well. Great. So that's where we complete our function to train the whole GAN model. Now what's left? The only thing left is to train the model. We are having the training dataset which is ready. The total number of epochs for which we are going to train it, I'll just keep it as 5 epochs for the demonstration purpose. And later on, I'll just post the whole epochs. Like, for example, I'll be choosing 500 epochs. So, okay, you can choose 2000 epochs as well to get even better results. But yeah, just to get initial results, I'll train it for some epochs and post it at the end. But yeah, just for understanding how it's going to work, I'm going to train the model for a few epochs and show you how to restore the checkpoint, right? So yeah, stay tuned for that. I'll see you in the next video, guys. Thank you so much. So to train the model, I'm going to call the function that I had built in the previous video. Going to pass the data set and the epochs I haven't yet defined it. I'll define it on the top. My epochs for now is 5, which can change later on. Okay, so I'm going to run this code cell and finally run this. Hopefully there are no errors. Okay, we have got the error. TQDM is not defined. I guess we had defined it over here. I guess I forgot to run the code cell. Yeah. Now let's try to run it. So this is indicating how much amount of percentage of the steps are completed. Okay. And I guess again we are having some error. Let's try to see. Real output is not defined. Okay. Let's check where it is. It's instead of the training step. Real outputs, fake outputs is there. Name real output is not defined. Oh, it's in the cross entropy. Okay, I forgot to check that. Real output. Oh, I need to give fake output over here. Okay, my bad. It's just the same thing, right? The same shape it will be there. So now let's try to train it. One more error. Add gradients. Where have we used add gradients? Add gradients. Oh, it is apply gradients over here. I'm sure most of you must have noticed this, but yeah, while coding it, we don't really notice it. So it's completely fine. We can do this kind of changes at the end. Hopefully, no more errors, man. Or else we are going to solve all the errors step by step. No need to worry. One more error. Let's see. So now it's about the shapes. Okay, incompatible shapes 128 versus 0. So now this is going to take some time to figure it out what's the problem. So I'll just pause the video over here and get back to you once I get the exact idea about where we did some mistakes so that the video length is not expanding. Alright guys, welcome back. So as you can see that our training has begun and there are certain changes that I have done in the codes. First of all, I restarted the whole notebook because I was running my code cells here and there to demonstrate you something. So I just restarted everything. But then I saw that it was taking a lot of time for the training part. So I've just made sure that I've turned my accelerator on and I'm currently using GPU P100. And per epoch, you can see that it's taking approximately 10 seconds. And this is the result of PQDM. It's showing us the progress. So this many steps are to be there in one epoch. And then one epoch will be completed. And the changes that I've done in the code to solve the errors, by the way, the first one, like, after doing the restarting of the whole session, I had to get the error over here because see, this was the code cell that was on the top. So it said that the TF is not defined. So I just interchanged this order of the two code cells. Apart from that, the second error that I had found was over here in the discriminator loss. Instead of the fake output, I was having a real output. And then after having that solved, my training is going smooth as you can see over here. And then I've also changed my epochs from 5 to 20. What is the reason behind that? Because I also want to show you the outputs that I'll be seeing in the output folder of Kaggle in working directory. So yeah, for that, we are just going to see what kind of outputs do we get over here. I'll just tell you one more thing by the time this training is happening. Just in case if you are not able to see the session options over here like this, in that case, what you can do is you can go to your Kaggle, then from the top right corner, go to your settings, and over here there's an option of phone verification. Please make sure that you have done the phone verification without any kind of issues. Only after that you will be allowed to use this kind of accelerator. So yeah, just make sure, just in case if that's not visible, you do that step. And then in the table of contents, all the steps that we have defined, right? We get access to it. And okay, I'll just cancel it. I don't want to hamper this process. And then step 5, yeah, it basically scrolls through the whole thing. That's great. We are just one epoch left, but you can see that already we are having some good results. That we're at least able to see something. Obviously, 20 epochs are nothing. I'm going to train it for at least for 500 to 1000 epochs. And I ask you to go ahead and run for as many epochs as you want. And you will see that the results have started to appear. Okay. So right now 20 epochs have completed. And this is the output that we are getting by clearing the last epoch and then still having the outputs from it. And if I show you one thing now over here, if I refresh this, you can see that images per different epochs the way we wanted according to the four digits decimal places. That's what we are having over here. Okay, so you can click on the training checkpoints to get the idea about the checkpoints that we are saving, where we are having information about our models and the optimizers. Okay, let's if you want to download this into your system, then how can you do this? Either you can zip all this kind of this things together in one folder, or else you can click on oops, you can click on save version. You can click on quick save, advanced settings, always save output when creating a quick save, and then you can click on save. Okay, so it's going to work for you over here. You can close this up. Once it will be ready, there will be 1 appeared instead of 0, which means that you have saved the version. All right, so you can see that 1 is appeared now. I can click on this 3 dots, click on open in viewer, and then you can go for the outputs part, and that's where you are having the information that I was showing you, right? You can download it from here. And let's say if this is the one that you want, any kind of file that you're looking forward to, you can go ahead and save it into your system and then see the data that is present inside it. All right. So yes, guys, that was about understanding how the training is going to happen. In the next video, I'll show you the outputs after training it for certain number of epochs. Okay, I'll probably uh, do 1,000 epochs and show you the outputs. All right.
So our notebook has already trained for 1000 epochs for generator and discriminator. And you might think that this is the output that we've got. The answer is incorrect. Okay, this is the actual data set. This is how the real data set is going to look like, from the above code cell. If I show the final outputs of the training, this is what we have obtained. Okay, as you can see that this is not a really high quality and diverse outputs that we are getting as compared to the data set that we are having. Just look at the diversity of the data set. Only similar kind of images are being produced as a part of the output. After 1000 epochs, this is the kind of result that we are getting. Per epoch, it's taking approximately 10 seconds. So for 1000 epochs, it's going to take approximately 2.7 hours, 2.7, 2.8 hours. And the outputs, according to the outputs, the conclusion that I've written over here is that clearly we can see that the model is not performing that well. And similar samples are being generated, indicating the mode collapse. And let's see that how we can fix this issue with the help of a different version of GAN. With the help of gradient penalty, we're going to learn this in the upcoming module, where first I'll be teaching you about the concept, because there is slight difference in the concept of WGAN as compared to a base GAN. So I'll show that to you in the upcoming module, and just look at the result that we are getting after 848 epochs only. Just look at the diversity of the outputs. We are clearly able to see the disks and this kind of circular galaxies, irregular galaxies, right? This kind of disks are visible. Even the features of the galaxy over here are visible, just like how we are having in the original data set. If I can show it to you. Yeah, just look at this kind of disk, similar kind of disk we have generated somewhere over here, right? And then this kind of outputs are also present, right? This kind of outputs are also there. This kind of outputs are also present. So just look at the power of WGAN. Okay, so more about this I'll talk about in the upcoming module. I have already keep this code ready over here for you guys, because the code is more or less just the same, just a little bit of optimization, and that's about it. I'll explain more about that in that respective module. But yeah, that's what you're going to generate with the help of random numbers. Just think about it. With the help of random numbers, you are getting a data very similar to what you are having in your actual data set. Isn't it just crazy?
So yes, that was it about the second module over here, guys. And I hope that you got the idea of how to go ahead and set up your traditional GAN with the help of Keras framework. Now, the problems that we have faced with the GAN, we are trying to sort it out in the upcoming module by understanding an implementation of a different version of GAN. So yes, I hope that you are very much excited to understand that how we can solve this kind of problem that we face in the traditional GAN. And it's not that I cannot solve this by just doing some kind of changes here and there, but that's a very painful process. And therefore, I'm going to introduce you to a whole different version of GAN that is made to solve this kind of problems that we face in the traditional GANs. So yes, I'll see you in that next module.